Hey, good
Alex.
afternoon.
Hi, Maite.
Hi.
Hey, Robert.
Okay, well, I can't hear you.
Hello.
You can't hear me? Still?
Yes.
You can hear me.
Oh, now it's working. Sorry.
Okay, that's all right.
How are you, Matt?
Okay, how are you?
Good, good. Yeah. Getting there.
Yeah, exactly. We're almost all there.
Yeah. Portfolio reviews and some exams and yeah.
Mhm. That's right. That's right.
Hi, Robert. Hi, how are you?
Hi,
Good
can
to
you hear
see
me?
you.
Is my audio?
Yeah,
Okay.
it
Hi.
is. Yeah.
I'm well. My face is a little off centered because for my birthday on Sunday, my parents got me a very, very long-lasting streaming monitor. So now the monitor is.
Well, happy birthday. Happy late birthday.
Thank you. It's
Yeah. Yeah, and I think Michael Garrison emailed, so I think he should be able to join in a moment. So he should be able to start more or less on time. Oh, great, Catherine. Good to see you joining as well. Maite, are you more or less ready whenever, at any time? I assume you're more or less ready to share screen and start at any time. Okay, great.
Yes.
Well, I would say it might be worth going ahead and us kicking off already, Maite, just to have more time. And when Michael Garrison joins, he joins, I think, since we have 3 or 4 faculty members here at the moment. I think it's worth probably going ahead and kick off if you don't mind, just in the interest of keeping today from running too long. So yeah, and just as a very brief reminder to everyone, we do have 3 Thesis A presentations, which are after primarily the research phase of the thesis, and so those are meant to be conversations, the presentations, and therefore the conversations are more about next steps and how to proceed into Thesis B, the execution of the thesis work. And then the 4th presentation is Robert Lehr, who with the Thesis B, which is his final thesis work. And so the nature of the discussions might be a little bit different for the first 3 and the last one. But for these first 3 in particular, it's meant to be just a productive conversation. And so as I mentioned in the email to you all, I recommend trying to keep your presentations from running too long. So effectively, it's your 45 minutes to spend however you want, but I recommend keeping a little bit shorter so that you can get more feedback to help give more ideas and inspiration and just criticism to respond to going forward in the following semester. So that being said, Maite, I'll go ahead and let you share screen when you're ready. And I'm going to start recording, and I'll let you also just, I think most of us probably know, introduce yourself and who your thesis committee is. And you're still muted, by the way, Maite.
There we go. Okay, can everybody see my screen?
Yeah.
Yes.
Okay, so, well, hello, everybody, and thank you so much for being here. My main topic of my research is the cooling potentials of natural ventilation integrated with vertical greenery systems. And so my advisors are Dr. Faulkner and Dr. Vajreshwari. And so my main research question is, what are the cooling potentials of natural ventilation integrated with vertical greenery systems in urban residential areas in Austin to mitigate urban heat island, reduce buildings' cooling loads, and improve thermal comfort conditions? And so my methodology was, as this semester, focusing on the research and focusing on the lit review, trying to analyze and research climate change, urban heat island, passive design strategies, greenery systems, and natural ventilation, and try to figure out and select my specific site that I will be analyzing. And next semester, I will be moving on to modeling and doing all the simulation with MBMed software, starting with modeling the existing site conditions, and then my retrofit and proposals. And finally, we reach the simulation results and analysis and conclusions. So for this presentation, I'm going to take you kind of starting off by the problem and starting why this research matters, and talk about climate change and urban heat island and the different impacts this has on ourselves and the environment. And then I'm going to talk about the building typology that I've chosen, kind of why I've chosen this residential single family and retrofit project specifically, and then explain my methodology for finding the site. I'm going to talk a little bit about the proposal, mainly focusing on greenery systems and green walls, and then conclude with my future steps. So throughout the presentation, I'm going to be taking you through different scales, kind of starting with the world perspective, going into cities, into neighborhood, and all the way down to a single building. So to start it off with the problem. So the Earth our planet is heating up, and it's heating up really fast. Since 1880, the world temperature has increased by a little more than 1 degree, and 2/3 of this increase in temperature has occurred since 1975. And scientists agree, and the greenhouse gas emitted by human activity are the primary driver of this, as they trap heat from the sun and they heat up our planet. And as you can see in the graph here, energy is largely responsible for this. And 39% of the global carbon dioxide emissions are attributed to the built environment. So we really need to take a hard look at the way we are building our cities and designing our buildings. This has, and we have seen this impact and changing, and it's causing long-term changes to our weather. And we have seen these extreme weather events with major increases in wildfires, in heat waves, in drought, with 50% increase in severe storms, and floods, major floods have more than doubled. And with 7.8 billion people on the planet and 55% of the world population living in urban areas, this is really changing the way that our environment is working. And it's really the growing population density simply exacerbating the environmental degradation. And with more the cities expanding and making more room for impervious cover, there's less space for nature. And cities are particularly impacted with this phenomenon, the urban heat island effect, which are higher temperatures registered in urban areas and in their corresponding surrounding suburban and rural areas, which are largely due to land surface modification, human activity, vehicles, buildings, and materials, which differ greatly from the ones that we find in nature. This is, again, really impacting us. It's affecting people's health and well-being. It's deteriorating thermal comfort. It's worsening the air quality. It's increasing the intensity of heat waves, and really increasing our energy consumption. Now, the US, which is the third largest population, has the third largest population, and 80% of its population living in urban areas in more than 310 cities with population over 100,000 people or more. It's really, really important that we take a hard look and try to make cities a better place to live. And the CDC projects the number of days above 37.8 degrees Celsius or 100 degrees Fahrenheit to continue to increase. And I think these images are really impactful and a strong reminder and telling us how the temperatures are simply going to continue to increase, especially if we don't start taking action now. And with about 140 million buildings in the US, while it's important to look forward and design better buildings and better cities going forward, it's also very important to look back at what we've done and the damage we have done and retrofit the existing stock and go back. And that's why I think retrofitting is so important. And what better place to start than our homes? So that's what takes me into residential buildings and to understand a little bit more. Residential buildings are among the top energy consumption sectors. And as you can see in the US, while the renewable energy has been increasing, it's still really dominated by fossil fuels. And residential is no different. It's only over 7% of the energy used in residential is renewable energy. So we really need to understand and find ways to reduce that. And so looking exactly at how it is that we are consuming the energy in our homes, 32% is attributed to the HVAC system. So for both heating and cooling purposes, being the largest energy consumers. And additionally, in this survey that was done in 2015 by the Energy Information Administration, 1 in 3 households reported facing a challenge in meeting energy needs, and 11% reported keeping their homes at an unhealthy or unsafe temperature, really showing how impactful and how meaningful it is to go back and look at our homes and find different ways to both retrofit them and finding different passive design strategies to make thermal comfort better, to reduce the temperatures during the summer, increase them during the winter. That takes me to the site selection. So as I mentioned, I'm looking at Austin. And so as you probably all know, Austin is considered to be a humid subtropical climate, which is categorized by long, hot summers, short, mild winters, and warm spring and fall transitional seasons. It's basically a cooling dominated climate, which with all of this global warming is just going to continue to get hotter and hotter and hotter. And as we can see here from the projections from the CDC, the number of days above 37.8 degrees Celsius, the consecutive days above this temperature are just going to continue to increase, making it very important to find different ways to cool our neighborhoods and our buildings. That took me to this very, very interesting analysis by Bizcarguenaga and Yang of climate vulnerability in Austin, multi-risk assessment, where they analyzed, on the one hand, the social vulnerability of the population in Austin, and tried to understand where it was located in Austin, looking at people's age, income, education levels, and so on. The one hand, and then looked at the places that were receiving more heat, and that was matched with places that had less tree cover, and put together those two indexes to create this really comprehensive heat risk and social vulnerability index that I analyzed. I took that map and that research and overlaid it with the current zoning for Austin, because I wanted to understand where were the single family areas that were most impacted by heat, and also by with social vulnerability. And so these are the ones when looking at the score. So the Bizcarguenaga and Yang have a score of 0 to 1, 1 being the highest degree of vulnerability. And so I started by analyzing these places that were in 0.5 to 1. You can see, and there's no surprise, it's closer to downtown and to the more urban areas. I then increased it to 0.6 to try and reduce the number of areas and try to find a single one. That gave me 67 census block groups with a population in total of 143,000 people and 52,000 residential units. So I really wanted to continue to narrow down and find a single location. And to do so, I looked at the mean population and mean residential units by census block and eliminated the ones that were at both ends to try and find a more representative block. And I also eliminated from the map the locations that had only the social vulnerability index below 0.5 or only the heat risk below 0.5. That led me to this 26 census block. And from there, what I did was try to analyze which ones had more, a bigger ratio per se of single family homes versus commercial. So I selected this site right here. It has a index of social vulnerability and heat vulnerability of 0.66. It has a population of 1,566 people and 577 residential units. So that would be kind of at a bit of a wider scale, at more of an urban scale, the site that I'll be analyzing here in Austin. So it takes me to my mitigation strategies and what it is that I intend to do. So going a little bit back and rewinding a little bit. So we have a problem. We have more cities with more people, with less nature, causing urban heat island, increasing temperatures, increasing cooling loads, increasing energy consumption. In turn, it's increasing the greenhouse gas emissions and leading to global warming, climate change, extreme weather, and again, extreme heat, which heats up our cities again. So we are in this never-ending loop. And so where I'm trying to change things is trying to increase nature and bring back nature into our cities. And in a way, it's sort of going a little bit back to basics and look at what we have and start taking from nature and start giving back. And yes, again, just bringing nature back into our cities. Now, greenery systems have so many benefits, and nature in general, from reducing noise and air pollution to helping with stormwater management, absorbing CO2. This is improving thermal comfort, improving urban environments, improving people's health and well-being, improving urban biodiversity. It's really mitigating urban heat island and reducing the energy demand we need for, especially for cooling purposes. And while it is, and as I mentioned, it's hard nowadays to find place and find space for nature in cities specifically. So I am proposing to add this greenery by adding green walls. And specifically, well, green walls can be categorized into two systems, green facades and living walls. And I'll be focusing on green facades, which really are green facades, they're really looking at solely at climbing plants, whereas living walls are more this complex systems. And so I argue that these systems are trying to bring greenery to a vertical surface by implementing very hard and expensive and complicated systems to operate when nature already has a plant that is climbing vertically. So I will be focusing primarily on both direct and indirect green facades. And so what I'm proposing is at two different levels. So there is one level that is more at an urban scale, which I want to analyze how adding this greenery to a neighborhood is going to improve that microclimate and reduce the air temperatures outside, therefore also kind of improving the potential for natural ventilation and just reducing that air outside in the city. And then at the scale of the single building or single family home, I'll be analyzing this impact in two ways. Now I know that green facades, while they do have kind of a bad reputation about being very damaging to buildings and to the facades, which is not necessarily true. It is true for certain materials. So I want to analyze it in two different ways, kind of this green facade and the second facade. So the green facade, having the plants directly grow on the building facades when it is possible, when the material allows for the plant to naturally grow on the facade, and see how that's protecting and creating this buffer, and see how that impacts the interior and cooling loads of the building. And also creating a second skin for the buildings that cannot could not have the plants grow directly on their facades, having a very simple mesh where the plants can grow. And I want to understand kind of this shading and this second skin and what the temperature will be between the facade and the green wall, and how the air that could flow in between, would that or wouldn't that kind of help reduce the heat that the house absorbs, therefore reducing its cooling loads. So finally, my future steps are modeling this through MAAD software to really analyze this idea that I have. And so I'll be modeling the site, as I mentioned, and then modeling these different retrofit proposals and reaching my conclusions next semester. And general anticipated findings, I guess I expect the added greenery to reduce the urban heat island effect and improve the exterior air temperature, therefore improving the cooling potential of natural ventilation, and decreasing the building cooling energy load, and improving therefore improving the environmental footprint of buildings, and overall improving the humans and other species health and well-being. And that is kind of my general concept. So thank you.
Thank you. Great work, Maite.
Thank you.
Could you go back to your site screen?
Yes,
or slide?
This one?
Yeah, I couldn't on this. I know what site you're talking about, but I couldn't see the street names. Maybe for the others, you could describe a little more exactly where this is in Austin.
Yes, this is, so let me go back here, downtown. So UT is about here, downtown is right there. So it's this little area right there. And so it's between First and 5th Street, and between Chicon Street and it's and Pleasant.
Pleasant Valley, yeah.
Yes.
Thank you.
Yeah, no problem. Yeah, which my site, I guess, if I had any questions or wanted to pick your brains, would be a little bit on the site, because if I go back a couple of slides, even if I go maybe here, I ended up choosing, so I narrowed down the different locations kind of very methodologically, but when I really got to this last couple of spaces, of course, I'm looking at single family residential, and that's the typology and the buildings I'm chosen to analyze. And so that's why I ended up choosing that specific site, because it does have a commercial area, but it's not as big as, if you can see this sites up here, more to the north, they have a really, really big part of that area that has a commercial or big. So this section right here has a big sports academy or something like that. So it does make sense that the places or the locations that are most impacted by heat would be next to this big box or big commercial areas, because they have such a big impervious cover for parking. And of course, in that sense, it truly makes sense that this would be the areas that would be most impacted. And I ended up choosing the other one because it had more single family, but ultimately, maybe it makes sense to look at this other site, even though I'm not really trying to look at commercial, but it almost seems like the places that are more impacted ultimately by heat are commercial areas, more so than residential, which also makes sense. And you have front yards here and trees and whatnot. So I was really a little bit questioning and going back, and I was very certain about the site I selected, but then this past couple of weeks I've been kind of thinking it over, and maybe it makes sense to analyze how these changes would be in this area that has this big commercial part. I'm not sure. I don't know. What would you think?
You know, this is not, I'm not really on your thesis committee, but just as a faculty member, I have two suggestions. Number one, I think if you actually look at where the real impact is, it's along the highways for heat island. One of them is you could look at the heat island effect as you begin to talk about. And I think one way to do that is to actually get out into the field and try to see if you can find some examples. I know you had the San Jose Hotel, but maybe there's some examples that you could look at that would begin to look at microclimates that you could begin to see the difference in temperature by going out on a cold day or a spring day or a hot day and begin to measure the differences in temperature that are affected by green walls. I've been involved in a project that with PLE for some people who are doing that at Oxford. It's pretty interesting kind of work that they're looking at doing that, and so it you know, you're actually having to get maybe the hobos and go out and actually do some field measurements to begin to look at that, and it's really quite amazing from the preliminary data that I've seen, the difference in temperature between one and the other. But more particular, it's because they're absorbing sunlight and transpiring moisture and things like that. They're changing humidity. But it would be actually looking at the winter because of the way that, especially on clear nights where you get night sky re-radiation, that the actual green walls began to affect the heat transfer in that regard too. So looking at it in summer and winter. The other one, in terms of heat island, in terms of temperature and humidity. The second one would be the Villa Verde project in Mexico City was taking this sort of idea of green walls and doing something with it. And they did it along the highways. And that is they planted all these green walls along the viaducts and the highways on the inner side of Mexico City, and to see if it actually changed the air quality because it's absorbing CO2 and particulate matter and producing oxygen, and to try to get an idea if that's a way that they can control some of the smog problems that they begin to have. I think that's another area that you could begin to take a look at. I think from the preliminary stuff that I saw from Villa Verde, when they tried to do it along the major highways, it made a psychological difference, but didn't make much of a air quality difference. But it would be good to see if you could do that in the neighborhood. But those are two different pathways: temperature, humidity, and air quality. Okay.
Yes, I'm very familiar with that Villa Verde project, and I heard that the quantity of cars that go down those roads are just so big that really the impact was it's more psychological than physical. And also they changed at the last minute. They changed the type of plants that they used and changed to plants that didn't really take so much CO2 as others. They're different plants can filter the air at different rates. So
yeah, I've done a house in the neighborhood you're looking at. So I know it's a different type of climate. So maybe it makes a difference there. I don't know. But it'd be good if we had some data.
Yes.
Maite, could you tell me again? I know you were considering that site to the north. I guess maybe that's Runberg area. Was there another site you were considering as well, or
not really? I think that would be the other site that I'd be considering.
Maite, a couple of points. Again, like Michael, I'm not on your committee, of course, but just a couple of suggestions.
Well, that's why we want to hear from you all.
That's exactly external folks. So go ahead.
Of course. Yeah. So first of all, I think this is a great base for your research, really well put together, a lot of background information, and I think you're on a good path. And a couple of things that are maybe not connected, but first of all, like when Michael was talking about the heat island effect, I was thinking that you were also concerned with the cost of associated with the energy that we use for HVAC, right, for heating and cooling. So this was another aspect, and I was wondering whether your choice of residential buildings wasn't slightly related to that's where those two issues kind of overlap, and they aggravate the social, effects of excessive heat and excessive bills, right? So
yes,
maybe that's something to clarify. Which of those is important to you, or both of them? The second thing is, maybe it would be really interesting to say how you're going to use the site. Is it because you're gonna do analysis, as Michael was saying there, and how you're gonna do it? What is your equipment going to be? etc. Like, so it's like kind of trying to simulate a potential series of analysis and plan them would be really important, because I doubt whether, the size just for design probably matters a bit less. It becomes really just like a site. You could do it anywhere, especially if you're talking about using a software to simulate the effects, right? So that to me would be important. Like, what's the importance of this site? The other thing that came to my mind was, we have the thermal lab. Maybe that's excessive, but I could totally imagine you planting, green walls in front of one of those boxes and doing series of thermal analysis studies. So that would probably take you somewhere, else. But anyway, just kind of throwing it in here. And then two more things I wanted to say. So when you mentioned digital simulation. Now, I don't know exactly where the NVNet software is now in terms of the precision and capacity to actually model vegetation, the trees. I know that they're supposed to release some kind of tree module that will be way more sophisticated in 2021. But it's an interesting thing, like to even think, that could be, to me, like the focus of your work. Like, how much are we capable of simulating those dynamics? How reliable are those softwares? I had a friend at Harvard GSD when I was doing my PhD who was actually working on that. She developed a whole system of analysis of plants for digital simulation in order to be able to work on the green walls. I can share her name with you. I don't know how much you're interested in that, but I think the issue of the simulation engine is really important. And the last point I wanted to mention was that when it comes to implementation, the implementation of this kind of systems, especially when you're talking about socially disadvantaged areas, a lot of that has to do with cost, right? And so something that when I did my own research and I looked at incentives, I was really shocked to see that I found one single incentive among hundreds that actually subsidized the purchase of trees for shading. And that was, like, this was in California, but it kind of repeats everywhere, right? So, and it's, in a way, I think that's an important issue to consider. I know it might not be part of your project, but it's important. And also what's important to me is also how the regulations look at plants. So as far as I know, until now, plants are not considered as part of the official kind of shading or energy managing elements when it comes to modeling the building. So yes, they will tell you, you can put plants, they're beneficial, but you get no points for that. So all of those kind of mechanisms really impact why we often don't use those systems, especially when there is not an architect, and that's very often where we're looking at single family housing that is not designed by an architect for a wealthier client. So I think that's all I have to say, but I hope it's useful.
Very useful. Thank you so much. And definitely the cost is something that has been very present on my mind, I think. And even looking at people can't afford to pay their bills and everything. And I mean, reskinning the whole building and making it super airtight and changing your HVAC and doing all these things, those are all fantastic if you can afford it, if you have the time, if you can do that. So I do think that we need to find also ways to more or non-invasively retrofit our buildings, and the wider range of possible solutions that we can offer and passive design solutions that we can offer, maybe the more people really can start implementing them. And so that is, and definitely the cost is something that's really been on my mind. And that's also why I'm not really looking at living walls and focusing more on green facades. Also has to do with the cost. So that is definitely a really big part of that. And I do need to start looking a lot more into NBMed. And that would be my next step, sort of to really analyze and see how, as you mentioned, how accurate and exactly how it is that I'm going to be able to analyze all that and measure it. Yes.
Yeah, and you should mention, Maite, she just got the software, she and Diamond, through a Green Fund grant. So they're just now going to start using it. So they haven't had a lot of experience with it yet, but they have done a lot of research and a very thorough literature review about other research projects using this software in order to calibrate it a little bit. To Professor Garrison's point about microclimate, Maite was also in touch with the city, where they are putting up sensors and monitoring temperatures throughout the city. So maybe overlaying some of that data could also help.
Yeah.
Yeah, I was thinking, I have a few thoughts that somewhat relate to some of Michael and Alex's comments, and maybe take a little bit of a different tack as well. So first off, I think that your presentation, I appreciate the fact that you really composed a presentation for this, both graphically and verbally. It was extremely clear, actually to the point to where one of my recommendations would be, heading into your Thesis B presentation, a lot of what you've done could be compressed down, and for the sake of this audience, when you're preaching to the choir, I think that you clearly established the context and the premise of climate change and the problems that come with that. But I think that if for a different audience, then maybe there is a more, expand that more. But I would say for the sake of your final review, that could be condensed down to a very small amount to make that point about the impact of climate change, and then how you bring that down to the scale of the house and the consumption ratios within the scale of the house. So it's important to make that leap and that jump. But I thought that all worked really well here, and demonstrating the point that it cuts across different aspects of sustainability, both from energy consumption as well as health and social factors. So acknowledging this trend generally is something we're all aware of. You're also doing a good job of showing how extreme that trend is, and heading forward. And then also pointing out this acute vulnerability in this particular part of the city, I think is a good strategy overall. I also think it's a pretty good strategy to approach the retrofit as opposed to the integrated system. For the sake of your thesis, and that's not to discount the integrated system, which has a lot of value, and I think you're acknowledging that, but just the widespread deployment of that is limited. The same way with green roofs. We talk about intensive green roofs. It's a very involved thing to do, and it's quite expensive to implement. And it's one thing to make the point that green roofs could make a big difference, but the difference between the intensive and extensive green roof is substantial in terms of deployability. So I'm on board with all of that, and I think the question becomes, site choice is important, and I'm glad you asked that directly. I wonder if, because this is partially a question about optimization of surface, and both in terms of type of surface, but quantity of surface, you might take a transect that has both some commercial and residential. So to show the difference between a big box and smaller scale residential structures, and maybe some that are in between, because obviously the larger of an envelope that one has, the less surface area we have to volume. And then vice versa. Smaller structures, you have a lot more surface area that could, have greenery applied. And so I'm wondering if that's maybe a good strategy to actually, for that to be part of what you're demonstrating, is the difference that it might make in terms of how much surface area, what the different types of configurations that, how that might make a difference. I also think, and this might relate a bit to Alex's point about the limitations of the software. Clearly you want to acknowledge that very directly, what the limitations of the software are, and then think about, and I don't think you mentioned if there would be a field component to this. So when Michael brought up the idea of the field component of actually taking, actually measurements, taking temperatures in different parts of town, different solar orientations or different parts of your chosen site. I'm not sure how much you imagine that to be the case, but part of your thesis could be about the validation and the compare and contrast to what the software is telling you in terms of what the differential should be in temperature based on all the parameters that would go into the software based on what you're measuring in the field. And if you were to simulate some sort of green facade deployment, even for a small area, to test that. But the main 2 points I want to make to conclude here is, one, is that there's an interesting conflict between introducing impervious cover and density, especially in this part of the city. And on the one hand, impervious cover limitations are there for good reason, and it's not. That's actually less to do with urban heat island effect and more to do with just managing stormwater and floods. But those two things could be interrelated, and the conflict there is, I suppose one thought I had was, what if you were to make the argument, what if the impervious cover limitation changed into where instead of being 45% with SF3, or at most of the area shown was SF3, if it were to increase to 55%, how much difference would that make? The flip side of that problem, which still relates to sustainability, is then you have less density, you have less opportunities to have auxiliary dwelling units and just increased density in terms of population and architecture or built form. So I'm not sure what's there exactly, but I would really think hard about what your ultimate argument is. If the ultimate argument, if it is more about only a retrofit scenario, or if you begin to, if you're suggesting potentially thinking about code changes in the future for other sites as well, if it's only about retrofit, I just think there's an opportunity there to think about those types of ratios and the pros and cons. And the very last thing is then the spatial impact. So I don't know if you imagine this, I don't know if you imagine the impact at the human scale, or if you imagine this being more of a quantitative exercise at the end of the day, where you're going to show percentages that you've dialed up and increase the amount of square footage of greenery, and the software showing that it could make the difference of X, Y, or Z, if that's where it stops, or since you're talking about the human scale and human factors in terms of health, if you begin to either speculate or simulate spatial implications as well, in terms of how those neighborhoods might look and feel different, even just at the scale of a pair of houses or at the street scale. So it's a bit of an open-ended question, but both of those, both in terms of, I guess there are two questions there. One is, do you imagine actually having field studies to validate or test the software? Or do you imagine it being more virtual? And then secondly, do you imagine there being a formal/spatial component to this as well?
I would think I would like to have that spatial component to it. I don't know if that's the architect in me wanting to not just look at the numbers, but wanting to see something and yes, have that impact visually, and especially as you mentioned, how impactful and greenery has not only on this specific and this, it goes beyond that. So I think there's a big opportunity for it, and I would like to do that. Now for going out and measuring specific data, I'm not entirely sure at an urban scale. I had thought about using the thermal labs, but I think that's probably too late just to have them even grow out there. But maybe seeing if I can bring it to a different scale. But that would have been, I don't know if it's too late by now, but that could have been, or could be very interesting. But measuring it more at that urban scale, I feel like I would rely more on the software, or at least that's what I think at the moment, more than really going into the field at that scale.
Well, I do think you've got a good resource with Professor Garrison when looking at microclimate, which is what your topic. I think you're going between scales, which is what makes your research so interesting. You're looking at the building and urban both simultaneously, which is so important to do. But if you did want to just get a baseline, I do know that at the city, they offered through that participation project for students to go and they can loan you out some sensors to take data on your specific location. So there may not be a sensor right up against the neighborhood you're looking at, in which case you might consider placing one there. As far as growing the greenery, to make a comparison after, yeah, I agree with the time you have. That's maybe where you would rely upon the software, but getting some, like Professor Garrison said, some differences, time of day and all of these differences for that microclimate study, that could be doable, I think, in the time you've got.
Yeah, definitely. To better understand also how that software is, or how to calibrate it. So yes. Okay.
I'll put a link in the chat to another specialist who has a climate consulting firm in Canada, Myring Byers. He's a very good resource. You could probably email him. I'm curious still about your Toronto. You were looking at actually Montreal. No, you were looking at comparing. This is another interesting point. Maybe you won't have time, but at least in your lit review, you were looking at comparisons of where urban heat island can actually help in cold climates in the winter, and then looking at an extreme climate in Austin and comparing mitigation strategies. Is that something for future now that you're thinking about, or are you still going to consider Montreal?
I feel like if I do have time, I would love to integrate Montreal. I do think it's important to always look at, compare those two extremes in that sense. So while you do want to have those buildings next to each other, and you do want that urban heat island effect to help you through the winter in climates like Montreal, but also the summer, those northern locations are being more impacted during the summer because of the increase in heat. They don't have AC, they're not really prepared for that heat. I mean, here you expect that heat to happen, so you're better prepared than they are. And there's actually a higher rate of mortality, and people are highly impacted in those locations. So kind of looking at it from different views and different needs and comparing the two, I find to be super interesting. And I would love to have the time, but I'm not sure I'm going to have the time to look at.
Well, you've already done it in your lit review, and you've discovered that dynamic systems, so you can change between winter and summer for such cases, could be useful. So even if you don't model it, I think it's still worth leaving in your discussion and your lit review. Okay. It is an interesting point.
Okay.
I wanted to last briefly add, Maite, that I would recommend having a variety, a range, maybe a spectrum or a range of a few different quantities of increase of greenery. So for example, I'm imagining that there might be a tipping point at which it begins to make a real difference. And let's say, for example, the difference between 5, 10, and a 15% increase in green surfaces. There might be a big difference between one or the other, where to do with urban heat island effect, where suddenly if there are just enough, similar to how any buffer works, where if you have just enough buffers in place, then the heat can't readily be stored, or there just aren't enough places to be stored. It's like there's nowhere for the heat to hide, so to speak. It just can't accumulate. And so I would look for if you I don't know how the software works, but however you're applying this, is it sounds like it does have a formal aspect to it. You're not just saying increase by some random percentage. You're trying to find surfaces to do that. I would try to find maybe 3 different varieties and 3 different ranges that could potentially allow you to detect if there is a tipping point where suddenly now it can really make a difference by half a degree or a degree or 2, whatever the case is. It's just something to think about in terms of as you put this together, rather than just having one scenario that you've thought of bottom up, for example, or you've thought of, here's a scenario of just adding more greenery. And by the way, it might change the temperature by 0.28 degrees. If you could just sort of show some, I guess the part of the question is it a proportional relationship? Maybe that's the question I'm asking. That is it, you add X amount of greenery and it keeps going, is it always keep going the same way? Or is there maybe some sort of way that it begins to exponentially increase, having more impact, or the opposite, the temperature exponentially decreasing? If you just add a bit more greenery, that might be a very interesting conclusion to arrive at, or to disprove what I'm hypothesizing.
Yes, definitely. We'll definitely look at it that way. Thank you.
Great. All right. Well, thank you, Maite. And next
Thank you,
is
everybody.
Thank you. Great work.
Thank you.
I think we are right on schedule. Ben, assuming that you're all set. You're still muted. There you go. Yeah.
I'm all set. Yeah. All right. So my name is Ben Marshall. I'm studying dehumidification for buildings, at least a new type of dehumidification for buildings. My advisors are Juliana Felkner, Zoltan Nagy, and Michelle Addington. So what is the problem? Why am I studying dehumidification for buildings? The problem is multiple. The first, of course, is thermal comfort. So whenever you sweat, the reason why our bodies sweat is for evaporative cooling. Your sweat evaporates off your body, which to change phase from liquid to gas, it decreases the temperature in the surrounding region. So that's why our bodies sweat, and because we're trying to decrease our body temperature. And if the relative humidity outside is too high, then the sweat just can't evaporate off and our bodies will overheat. So what is relative humidity? Well, both of these glasses of water have the exact same amount of water in them, but one glass is smaller than the other. This is the same sort of principle that we get with air temperature. So the one on the left would be representative of a colder air temperature, and the one on the right would be higher. So the higher the air temperature, the more water it can absorb. And so you would think that, hey, the hotter it is outside, the more the sweat will come off of my skin and the cooler I'll be, except that sometimes you get really high relative humidities, even in hot climates like Austin, and along the coastal regions of the United States as well. So ASHRAE, which is the American Society of Heating, Refrigeration, and Air Conditioning Engineers, or ventilation, they have come up with a zone. This is the psychrometric chart. So this just shows the difference between water temperatures, air temperature, and the amount of water in the air. They've come up with a zone on the chart that kind of shows where 80% of the people who they surveyed were comfortable. Those temperatures are somewhere between 68 degrees on the low end and 82 degrees on the high end. And then below 0.012 humidity ratio, which is the weight of water in the air compared to the weight of the air. And so if you take a look at the chart, everything in that blue shaded region is what I'm very interested in, because the temperature outside might be perfectly fine. It might be the same as what you want inside, what your air conditioner would be providing. However, the humidity is too high. You'd be sweating, you'd feel sticky, and there'd be other problems. Some of the other problems would include mold. Mold is likes a lot of our building materials, and it needs it to be humid to grow. It needs water to grow, and it also likes dim light, but that's for another study. The mold not only can degrade the building materials, but it also releases spores, which is bad for air quality. You get lots of people who are allergic to mold. I've got a good friend who's allergic to mold, black mold, and it also gives you asthma and that sort of thing. You also can get water damage. So if you get condensation on your building materials, it might not grow mold. It might just get water damage, which will degrade your gypsum board and other materials in your building construction. So how do we get rid of this stuff currently, the water vapor in the air? Well, we use something called the vapor compression cycle for the most part. There are a couple different systems, but the vapor compression cycle is the most common for your residential houses. So how it works is that you pump refrigerant around a circle. You have an evaporator, which is the coldest one down here at the bottom. It is colder. The evaporator in your air conditioner is colder than the air that is being pumped through it. Same sort of thing. It moves that refrigerant around, gets compressed, goes to the condenser outside, the thing with the fan, and that thing is warmer than the air around it. Those two bits have to be colder and warmer than their surroundings, or else it won't work. So that's where we're getting into some inefficiencies. The reason why this works for dehumidification is condensation. So whenever the coil is colder in your evaporator inside, it's colder than the air, the water condenses on that coil and it pulls the humidity out of the air. There are other ways to do it. Desiccants are some. If you've ever bought a pair of shoes, it probably has a little pack that you shouldn't eat. Looks like a peck of salt, but it's actually silica beads. And those are solid desiccants. And what we do for these situations is we have a wheel that air is blown through with really high humidity. Those desiccants absorb it. And then as the wheel turns, the exhaust air from your building gets blown through those same beads as it kind of rotates through. And it evaporates that stored water. But it also, you have to add heat to do this. Liquid desiccants are similar process. They're just a solution. So salt water, if you get a solution very salty, it'll absorb water out of the air. So this is a quick, you don't have to understand what this graph means, but basically the two blue lines are the two different types of cooling, the amount of energy used. The one on the left is the vapor compression cycle cooling. The one on the bottom right there is the cooling energy needed for dehumidification with desiccants. It's a little bit better. It's actually supposed to be 60% better. The desiccant cooling is 60% better than vapor compression cooling. But I think that there might be another way. But first, why do we dehumidify without cooling? Like, why would we use desiccants over a vapor compression? Bless you. Well, its efficiency is one thing. There are several technologies out there that do not do dehumidification, but are more efficient than our current air system. So air is not very dense. You can move your hands through it. Water is a lot more dense, which means it needs a lot less in order to move a ton of energy around. So there are three different types of energy movement: convection, conduction, and radiation. As you can see, the radiative cooling is actually 60–70% of the energy that you lose in your body right now is because you're radiating to the walls around you, whereas only 30–40% is because of the air that's moving across your skin. This is great, but it doesn't deal with humidity, and that's why a separated system that deals with humidity might make this a viable thing for hot and humid climates, which would save a lot of energy. This is some radiative panels. They look just like some ceiling panels like you'd have in your office, but they are your whole not air conditioning system, your thermal comfort system. So it can be integrated into architecture very elegantly. Another system is the TAC wall system that's developed by NREL, the National Renewable Energy Lab, Oak Ridge National Lab. What it is it's a series of pipes inside your exterior wall that turn your whole wall into a heat exchanger. And if you set up your insulation correctly, you can direct heat from the exterior to the pipes rather than all the way through into the interior, which would decrease your heating and cooling costs. But it doesn't have a way to deal with humidity. Another reason why we want to figure out a way to separate dehumidification from your vapor compression standard cycle is because there's a lot of time in the year where where the temperature falls right where you want it. And you have to subcool that air before it can be reheated up to your room temperature. So you're losing a lot of energy. So if there's a way that we can use these times, this is a graph showing the temperature for every hour in the year. And the dark blue is the time when the humidity is above acceptable levels, but it's within those two temperature bounds that it's like, it's the Goldilocks zone. This is not too hot or too cold. So that's about 20% of the year mathematically. What about climate change? So these are, I've graphed out the years as far as how many hours, the hours from the previous slide, how many of those hours are there, even if we factor in desertification due to climate change. And we have about a 13% difference in the worst case scenario, which is the A2 scenario, but it's still a large chunk of the hours of the year, which this free cooling is available. Okay, so how do we solve this dehumidification problem differently than the way the desiccants have done it? Well, maybe nature has a way that it's already been solved. Throughout history, people have looked at nature and said, that's already been solved by nature. Let's just try to figure out the principles behind how nature does what it does. So this is a boxfish, and there was a famous study where they studied the geometry of the boxfish to try to figure out how to make their car use less gas, because the boxfish is super fast and the fluid dynamics around it work perfectly, but it was a really odd shape. So this is something they call biomimicry, to mimic what they see out in nature. So lotus leaves, these are super hydrophobic, which means they don't like water. Phobic means not liking or scared of. And so water beads up on the surface and rolls right off. And there are already some coatings that do this. That's chemically. What you're seeing here on the top right is a kind of electron microscope sort of representation of what is happening, which is that there's a bunch of little bumps called trichomes, and they touch the water droplets, but only in a very few spots. The surface area is very low, which means that the surface tension of the water does not let it fall apart, does not let it become unspherical. The contact angle stays very high. Well, nature's given us a way to do things super hydrophobically, which it rejects water. Nature also, using the same mechanisms, gets super hydrophilic, which means that it absorbs water. This is Spanish moss. You'll see it growing in a lot of hot, humid areas along the southeast United States. Along with ball moss, we have some here in Austin, as far as ball moss goes. They're both in the bromeliad family. They use trichomes, same sort of little bump things, but in a different way. Those are used to absorb water, to catch water in between the bumps so that it can't evaporate and the cells on the outside of the plant can absorb it. So is there a way that we can do this artificially? Yes, there is. At least I think there is. And according to my research, scientists have been using some of this technology, but for a different application. They've been using it to separate oil and water. So this is a image of these water droplets formed up on a piece of copper mesh. The mesh has been treated with to grow crystals that end up looking a lot like those little trichomes. And you can see there an image of the water droplet that's almost spherical because it's touching just very, very lightly. So here's an image of those dendrites, those copper crystalline structures that are grown or on the copper mesh. This is done several different ways. The paper that I am kind of basing my research off of does it electrodeposition, which is to run electric current through an electrolyte and grow the crystals onto the mesh. So what they found was, this is with them studying oil and water removal, what they found was if they passed a current through their mesh on the right-hand image here, if they pass a current through their mesh, what happens is the mesh, the outer layer oxidizes, reduces, and it creates a super hydrophilic. It really likes water. It pulls water into the mesh. It does it by this quick formula. Fairly simple. You add the 2 electrons, it breaks them apart, and you start to get some negative hydroxide ions, and everything kind of pulls in towards that mesh. So what about being able to, it's great if we can just soak some water in, but what about getting rid of the water? Well, the hope of my research is that there is an electrical perfect spot where you can cycle between super hydrophobic and super hydrophilic properties of this mesh so that the water pulling in gets pushed out, forms droplets, and gravity starts to pull it down the mesh, and it drains away just with the force of gravity. This shows the test that they did on their mesh sample, and there is such a point where if you modulate the frequency, it looks like around 7 or so hertz. That's cycles per second. And at around 30, 32 contact angle, you can get it to cycle between the two. So what have I done to date to start this? Well, I got a mini materials grant from the School of Architecture, and I bought, or the School of Architecture bought these materials for me to start kind of making this mesh. And I have made some for testing. So I figured out based on the paper how much I needed per batch. And here's some titration calculations. Filled it all up. Mixing it up. We're outside. I am wearing a mask because I am dealing with some sulfuric acid. It's very mild, but it is just a little bit. So that's why we did it both outside and me wearing a mask. So we've got a DC power supply. We're using it to supply the correct amount of electricity that the researchers in Canada use to make their mesh. And we've got samples. So these are the samples that ended up being correct as far as the correct amount of electrolyte solution. And then I also have a bunch more samples that were an incorrect solution, but I still kept them around because if I have time, I'd like to test them as well. And I'm in the process of building a testing apparatus, which is fairly simple. It's 2 pieces of PVC and a blast gate similar to what you'd have in a shop, so that you can close off vacuum to or open vacuum to a tool to suck away your dust. And I've got a little signal generator there, and I'm going to use that to do the Hertz calculate or the Hertz experiment, like I mentioned earlier. I'm working on developing with my cousin, who's got a 3D printer. We're developing a little blast gate that I can use to put the samples in and electrify them. You can see those two channels for electrical wires so that I can run them to the signal generator. This is kind of what the test apparatus will look like when it's in use. I'll have a fan at one end, humidity and velocity sensors in and out, and the signal generator in the middle that's trying to get that right frequency. All right, so this is a school of architecture. This is not a school of material science. So what does this apply? How does this apply to architecture? Well, there are architects who think that the skin of the building should be a big part of how we treat the outside. Maybe how we do the structure. The skin of the building is the most important part. I am beginning to think that way as well. And here are a few examples of some projects that kind of touch on this. One from our own Professor Ficus for his submission, or his firm's submission, to the Habitat for Humanity 20 by 20 dwelling, in which these blocks on the outside not only are a form of screening as far as privacy and light modulation, but they also filter air. This is all kind of in theory. One building that has gotten built, which uses the skin as the way to as the interface for thermal comfort, is the Philologische Bibliothek in Berlin. This is Norman Foster. And the skin of the building is where they have the lights and the HVAC system and that sort of thing. It's the structure for the building. So it is, I think it'd be great to have this screen system that I am researching to be able to be integrated into the architectural aesthetics of a building, and not just stuck away inside some closet somewhere where you can't see it. Also, another way that this product may be used, or this material may be used, is for water harvesting. There are a lot of places that are far from water. People have got to walk a long way to get to water. This is a project by Warco Water, in which they made, not only in digital form, but also in physical form, some architectural installations that collect water for the village. The two on the right are two in-place installations in which this netting is used to capture fog and provide water for the village, so people don't have to walk so far to get to water. Another is a fog tower, which is architectural, not really supposed to be lived in. I don't think I think this is more for agricultural purposes. But that is my project to date. Any questions?
Ben, could you clarify what that scale jump was? A big scale jump from the experiments up to what you showed for some of the case studies. Do you imagine that your final output would be, I guess there's two ways to ask this question. More fundamentally, I'm asking, how much more of the experimentation do you imagine doing? And are you suggesting that it would be somewhat of a, almost an analogous exercise, or some sort of metaphor that's scaled up to the building size or building scale, or that is it possible that you imagine developing it at this very small scale that could be just applied, like literally applied and scaled up as a building skin? It's unclear to me offhand what you imagine the final output to be, exactly how far you're getting with the material study, which is really interesting, by the way. And the argument, the way your build up to the argument that you're making, all of that was convincing. That the most unresolved or unclear part is the last bit with the case studies, which are also interesting, but not as clear of a continuum, as though you were then trying to make that leap that maybe you don't. Well, I'll stop leading the witness here and just let you answer that question, and then I might give you some thoughts on that.
Sure. So currently, I want to make sure that this copper mesh membrane dehumidification system would work. And so, but my eventual goal, how I envision this thing being used is being applied to a building. How I envision it being, if in the best case scenario, how I envision it being done for my thesis next semester is to do some little installation, where I build something little that someone can stick their head in, or that is, or that they can walk around and look at. That's actually actively dehumidifying. I think that's
Okay. So I think my main recommendation would be. So again, I want to give the other reviewers a chance to speak more before I gather some more thoughts. But I just want to make this point that I think it's okay for it to be something that's a little more speculative in terms of exactly how it might be applied. And your one scenario of application could be just that. This is just one test case. I think the power of any given thesis project or any given study that this is meant to be distinctly different than a studio project, which is a one-off that's for a specific site, specific context. The hope is that this is something that could have a wider reach across building types, across scales and beyond. I think ideally, and if thesis work might take a very specific site and analyze that, but then suggest that this could be something that has broader implications. This research could lead to more research and doesn't just end in one building of a one-off thing. So I want to highlight that I think there's nothing wrong with then going for some type of output. And I think that's, and I know you have both an architecture and engineering background, and I think you should develop something spatial and formal, as long as it doesn't come off as a one-off of that being the end result of this. But again, framing it as one specific instance or one test case, that maybe even from there you suggest how that could then be modified in terms of scale or application technique to then be used more broadly. So that's my first reaction.
I just want to echo that. I think that given the sort of experimental at the micro scale, and then going to something maybe like a shading of a window or something like that, a little shading that is the next phase up. It's sort of just like an application. And then from there, one can step up and say, oh, these are all the ways shading can be used or something like that. But I think there's a missing step, a scale here.
intermediate kind of application that could be scaled up.
Well, you had talked about making a screen for like a single family home, like a storm screen is a scale you might be able to get to in time. We'll see if you get there. But I also like your idea of putting your head into a volume. I think either one you could do, or even both, because you're making rapid progress. Great work, by the way.
Ben, did you come up with the hypothesis that this other research could be applied to dehumidification?
I did, yeah.
I mean, that is really, really impressive. I think this is really cool, and I've never seen anything like it in the School of Architecture before, which is great. I'm kind of out of my depth in being able to really provide much meaningful feedback to the with regard to the technology. But two questions I do have that I think would be helpful to contemplate in your final report would be, number one, how does this potentially compare in terms of energy expenditure to other forms of dehumidification? Is it, I mean, maybe you already know the answers to this, I don't know. Is it similar, radically more efficient, maybe less efficient, but has some other benefits? And then two, I think to me, the whole question of the architectural application it's almost like a whole separate project. I mean, on the one hand, you're developing this technology, and on the other, you're trying to figure out how you might use it in a building. And that is one really interesting way that it might be Sorry. Hopefully you can still hear me. Something happened to my, there we go, my screen. That's one really interesting way that it might be applied, but you know, there are all kinds of other potential really interesting ways, even if that didn't turn out to be the right answer. So, you know, one question that just comes up with regard to that particular application is, if this screen is hot, i.e. it's got, you know, live voltage applied over the surface of the building, you know, what are the implications of that? And I have no idea how much, you know, how much current we're talking about here, but those are just the questions that come up. But I think it's a really fascinating concept.
Thanks. That is something that's been rattling around in the back of my head. Is this is probably not safe for children, and it's, unless you figure out some kind of system for keeping everyone from touching it.
What voltage are you applying to it?
It's just 1.5 volts.
Okay.
So pretty small.
Yeah, it's
not enough to make ozone or anything. So
yeah.
However, that was with the mesh sample used by the folks up in Canada, which is small. I assume that with a larger sample, I might have to. It will probably scale. So I'm not sure yet. We'll find out.
Can I ask a question? I'm sorry.
I was
Do we have
muted.
time?
Okay.
Oh, go ahead. Go ahead, Alex.
No, go ahead. Go ahead.
Oh. First of all, thanks for inviting. Ben, I had one suggestion. I saw in your experimental setup with the tube. You kind of put this, and this is just a suggestion to make sure you get what you get out of it. You put the velocity sensors and the humidity sensors in that schematic at the wall of the tube. But at least the velocity one needs to be in the center of the tube, because the velocity profile in the tube changes, and at the wall it's 0. So you won't get much information out of it. And then also remember to look a little bit into Reynolds numbers once you start throwing velocity into a tube to create turbulent versus, and depending on what you want to create turbulent flow.
Yeah.
To get better heat and mass transfer. That's all. Other than that, thanks for the picture of my lab in the basement. It's good to see that it's still there. I like to see it.
Nothing's burned down. It's all good.
It's still living. Thank you. Great work, by the way. I'm glad to see electroplating. And I think I would echo what Michael and Matt said. If you could create a, like a shading, and what Julie said, a little bit of a shading device, like open a window and put it into a window, like kind of like those window units. I'm not sure exactly what the best way is, but showing something like that could let you open the windows and ventilate without humidify the inside, that would be cool, even if it's just conceptual. Because it needs a sizing. Like you may have to think about how big of a size that window needs to be to create an actual effect inside. But if you can do it without just letting stuff in, that's not a bad thing, like a water filter, basically. That's pretty cool.
I mean, another, potential application might be, I think that's really interesting, Zoltan, and you could think of a whole palette of potential applications, and it wouldn't necessarily have to be decorative. Like you mentioned radiant cooling and the challenges associated with that. If you could somehow integrate this, with a radiant cooling system where this could provide the dehumidification so that you don't get condensation on surfaces, and maybe it's built into the same panels, or I don't know exactly how it works, but it seems like there might be other applications like that too, that aren't necessarily visible or decorative.
Yeah, I think that's what Jason was just talking about, is what I want to suggest, not so perfectly and technically, but that I don't think you should be scared of using this, this research that you've developed to actually just resolve a specific issue, rather than necessarily create some kind of formal design solution just because we're in a school of architecture. I think it's perfectly valid to think about it as a technology or a material. So I would focus more on that, on the problem. And maybe what's interesting is really thinking about, or more important, thinking about the conditions in which you expose this material to humidity and how in those different conditions, what kind of benefits you're getting, what kind of issues you're getting. So I can imagine that, what Zoltan was talking about, the velocity of air, that will be very important depending where you put this thing, how this thing will be reacting and in different contexts, right? Different atmospheric conditions. Or maybe start again from thinking where humidity is an issue. So Jason was talking about the cooling systems, condensation that you started with. So maybe it's more going back and thinking where those moments happen and how that could be applied, rather than saying that it definitely needs to be immediately, a tower or this or that. I think it has way more potential as something that resolves an issue and is not necessarily visible. And I think that it's really great research, by the way, for exactly in the School of Architecture, where we often see things that are conceptual but not working. You have something that is working and you can really push it further. So I would really encourage you just to keep on thinking about how it functions and in what conditions, rather than what kind of architecture you make out of it. Yeah.
Another way to say
people, talk to many people, because different people have different views on your problem, and they have another, and they're not in your small, not limited mindset of what this could be applied to, and talking to many people helps you to broaden that mindset a little bit. Sorry, Matt.
No, that's a great point, Zoltan. I think a lot of the feedback you're getting is on a similar wavelength, and that you're really onto something here. I think that I think you're generally being encouraged to proceed with this, and I think that the risk of going for a very exploring a very, very interesting form is that it would bury the lead of this work, and that ultimately your lead is more of a quantitative one to do with performance and a numerical impact that you can actually demonstrate to show the difference in and the question for me is how far you go with this. But if you're able to show some difference in humidity level, and therefore if you reverse engineer or just imagine your presentation in reverse, that then ultimately it increases comfort level, decreases mold, so it's increasing health, increasing energy performance, all those types of things. Is the goal, and I guess this maybe gets a bit to what Zoltan's saying about the scale of implementation in terms of how big of a surface do you need for this to actually make a difference. But I think that's probably the biggest takeaway that you would end up with in your paper, thesis paper, is like how much of an actual difference does it actually make? You can then only speculate as to how much difference that would make in terms of mold and in terms of comfort level and those types of things. I think you could approximate those, but you that in and of itself is a very concrete, very it's a big accomplishment if you're able to say that you can change something and move the dial, just move it a little bit in terms of performance by something that you've invented from scratch. Is based on precedents, but of course it's something that you're really bringing new knowledge. I just want to come back to that and maybe one thing I was thinking about is if you can't resist exploring some formal techniques, you would have to hedge it a bit by doing a family of forms, just to suggest here's some different ways, and maybe it is, to Michael's suggestion, that maybe it is more of a canopy or screen type scenario, and then you could imagine that scaling up. But to take it away from being, once, as I said in the beginning, being about this one output, so that one doesn't associate what you're doing with, oh, well, if I have to do that application, I'm not sure that works for this, but suggesting that there are multiple outputs for how this could be. That I think leaves some latitude to one understands that it is both something that works in theory, could also be applied in different types of ways without pinning yourself into a certain scale or form or shape or what those types of things.
That's good.
Yeah, you could even take it to be like kind of extend that into thinking about, you know, like one really effective way to integrate new technologies into like an existing technological framework is to figure out what you can do a one-for-one replacement for. So, you know, maybe there are aspects in a building that are common already that you could somehow replace with this material. Like, you know, like, could you electroplate all the copper water piping in a building with this system and have it be the dehumidification system? Or could you put, I don't know if you can put it on other metals, but could you, you know, electroplate a steel frame with this stuff and like have it drain off the water? Who knows? There might be all kinds of things that you could come up with there.
Cool. I had never thought about that. Doing electroplating other materials. That'd be really cool.
Do you imagine, I guess that this is similar to what we were asking Maite in terms of application and, you know, testing in the field. I mean, clearly you have a lab testing component to what you're doing. I'm wondering if, I guess what I'm trying to think through for all of you really, all of you that are in Thesis A, is if there are any limitations to consider during the pandemic and possibly having some restraint in terms of what you can actually test in the field and having some contingency plan. I think that the majority of your work is a lab-based type of work that can be done in fairly safe means without, in other words, I don't think you'd have too big of an impact to do with our current situation. But I would just hate to see for some logistical reason put a hamper on that for you, since you've got good momentum with that. So are there any factors, or maybe just let's talk about that just very briefly as we wind down. Are there other limitations in terms of the rest of the remainder of the work that you foresee, or like as I was saying, contingency plans in terms of how this all comes together?
So Professor Nagy has been kind enough to let me use his lab. And I'm the only one who's using it. So there shouldn't be any problems as far as COVID goes. If the buildings are shut down for any reason and I can't do testing in there, the apparatus is only 4 feet long. And so I can pack it up and move it somewhere else, as long as Professor Nagy's okay with me borrowing some sensors for a little bit. I can pack it up and move it to somewhere else and do it here on my kitchen table if I need to. So I shouldn't have too many problems there. I think just finding the time to get to the lab and go do the work.
Well, and I think you should place all bets on that, or at least put the majority of your eggs in that basket and just kind of stick with that as the main pursuit, knowing that you should be able to continue with that. I was just trying to think if there's some other way, if there was a potential roadblock that you saw with that. And that's only because I see so much promise with this that I'm just wanting to make sure that you've thought through, you know, some logistics of that. It seems as though you have.
Sure. The only big one that I can see right now, based on our talk today, is trying to make this at scale. The testing bits that I have currently, and the chemicals that I have left, are enough for some small samples the size that I've been doing. But if I wanted to do something the size of a small window screen, maybe a foot by 2 feet or 3 feet, I'm going to have to find some more chemicals and find some other. I'm going to have to do some more work.
But is there any way that and I apologize for my naivety in terms of exactly how the science of this works, but and it relates a little bit to what I said to Maite as well in terms of software validation. Is there a way that you can, you know, begin to establish some proof of concept at that small scale and then simulate it at an intermediate scale once you begin to, you know, prove or disprove your hypothesis in terms of how well that's working? Is there a way to start to find out at what scale, you know, the scalar differential virtually?
I think so. Yeah, I think that should be, because I already have the data point as far as the electrical usage from this group up in Canada, how much power and current it took to make theirs hydrophilic. So if I was able to, and I also have several different sample sizes. So if I test them at different sizes, I should be able to sort of curve fit something and figure out.
That's what I would recommend, at least doing that. I'd hate for you to, take on either a delay to do with trying to acquire more chemicals and or a large expense or just those. I would first try to take the path of least resistance in terms of materials and methods to arrive at this, and just having that range of scale within a small scale. You probably can learn a fair amount there. And part of any thesis is acknowledging your limitations. You have to acknowledge that there are some conditional components and some circumstantial evidence that you're using. Acknowledge that you can't prove everything, but you can begin to speculate. And so that's maybe a bigger point for everyone to do with the thesis, is that, part of your thesis at the end of it will somewhat answer your research question and hopefully arrive at some conclusion there, and then raise other questions and leave room for more research, which sometimes is carried directly forward into a PhD. Other times it becomes part of a body of knowledge that others can pick up on and work with. And so that's the sort of thing where I think it's fine to reach a good stopping point and then determine that there's just limitation in terms of, there's a feasible limitations in terms of what you can do with this work, in terms of scalar replication, just how much you could test, but speculate as to what you think would happen by simulating virtually. So for what it's worth, I would maybe get as much mileage as you can with that, again, before taking on a huge large scale operation. I'll just say that I personally don't think that your thesis hinges upon that. That's not the crux of what you're doing. It can be proven probably at a smaller scale. It would just be a bonus to go beyond that. But I wouldn't let that get in the way. If you start trying to scale up to set up the operation and a new kind of test instrument, that maybe drifts too far away from the point, because this next semester will go much faster than you think. Once you try to start gathering data and start to write these chapters. So as long as you have some variability in scale, as you're showing, that's probably plenty more than sufficient. And then you can then skip to that virtual stage from there. I would recommend.
And just to pile on that, I guess is a word. But if you're comfortable with the equations of the problem, what people do is, things like scaling laws derive, and if you write the equations down, on one sheet, like everything, like humidity levels, dehumidification, electrical current, geometry, they are related. Like some of the things are in one of the other, right? And so if you start composing them, okay, what happens if, the area becomes 10 times bigger? Then some of the other variables needs to change, right? And so, or how do they change? Does it become 10 times bigger? Does it become 100 times bigger? And then it's the question, like then the question what Desiccant asked is, oh, what if, all of this, you answered, and now you need 1 volts, but maybe 10 times the size will need 100 volts. I don't know. Or maybe it's a frequency, but if you put the equations down in simple ways, and you get like, rules of thumb of what you would expect. And if you have small scale variations that follow that law, like you said, like very small one, a little bit larger, then that's worth a lot more, because it shows that you actually understand what you're doing. And the other thing, I mean, yes, it's nice to make it 5 times bigger, but you will not fundamentally find anything new other than solving other technical problems of how you electroplate larger things and how you run a bigger chamber and how you need a higher fan and whatnot. And then that, it's a nice technical problem, but it will not add anything new to what you're doing fundamentally. But if you understand the problem fundamentally, which, to me as an engineer, it's what are the 6 equations and which one of those makes sense and are important, and which ones can you neglect, then you can even just run some numbers through it and see how the curves change or whatnot. And that's cool. But for me, right, it's not a building, but it's still cool.
Great.
Yeah, I'm really excited about this, Ben. As I told you, if you can solve humidity in buildings, that's the holy grail. I mean, we can do passive ventilation, we can have cooling panels, but how to get rid of that humidity, we really need people like you working on this. So congratulations on great work so far.
Agreed. Thanks.
Definitely.
Ben. All right, and so Diamond, you're next when you're ready to share.
Yeah. So I am working on mitigation of urban heat island effects on thermal comfort indoors and outdoors in the city of Bangalore, India. And my advisors are Dr. Juliana Filkner and Dr. Catherine Libernick. So first I'm going through the objective of the why did I chose this, and then go into the just brief on the urban heat island effect, then look into what solutions I'm looking into, and give the next I'll give the description of the site which I selected, and then going to the next semester, the thesis B methodology. So my main question, the main question would be mitigation of UHI effect by utilizing urban vegetation, surface cover material by analyzing the scenarios to evaluate the thermal comfort and energy consumption of the building. The sub-questions will be how is urban spatial morphology connected to urban heat island effect, heat stagnation, and how to mitigate it with redesigning. How materials like concrete and alphite will affect the temperature difference in terms of heat storage capacity. So my methodology is first I did the literature study and then studied the case study on the city of Bangalore. Then I chose the 3 different sites which I'm going to use for creating scenarios in the next semester, and the results will be compared with the environment software, using the environment software. And coming to the main objective, climate change. To date, human activities have caused approximately 1 degree rise in global warming since the Industrial Revolution, and we are on a track of 3 degree rise in temperature. Limiting to rise of 1.5 degrees Celsius will require immediate action. To talk about the Indian projection, temperature in India has projected to increase approximately 4 degrees Celsius, and around 1.5 million more people may die in India each year due to extreme heat at the end of the century. So average number of extremely hot days around the country of India is presently over 35 degrees Celsius and are likely to increase more than 8 times per year up to 42.8 degrees Celsius. Next is population projection. The global population projection is going to surpass 8 billion by 2030 and hit 9.8 billion by 2050. And the growth of war urbanization has been extensively accelerating, and 50% of the world population live in urban areas. And India will soon become the most populated city in the world. And India population is expected to continue to grow until mid-century and is expected to increase to 1.6 billion by 2050. And 70% of the increase will be in urban areas. According to the research, this phenomenon could cause disasters to the low altitude areas that is in Asia, which are expected to experience a rapid population increase. Greenhouse gas emission. Today, we collectively emit around 50 billion tons of CO2 each year, that is 40% higher when compared to 1990. And 73% of it is from energy sector. As in case of CO2 emission in India, it is the 3rd largest emitter of greenhouse gas emission after China and USA. And continued high emission of greenhouse gas has projected to lead to 4 degree rise Celsius in average annual temperature in India by 2100. Coming to energy consumption, the global average per capita energy consumption has been consistently increasing. Average energy consumption has increased by approximately 45%. The fastest growing growth in building energy consumption through 2040 will occur in India. And delivered energy consumption for residential and commercial building in India is expected to increase by average 2.7% per year between 2015 to 2040, more than twice the global average increase. Air conditioning is a major absorber of energy in residential and commercial sector in India. So looking into the air conditioning system in India, about 2.8 billion people living in the hottest parts of the world, only 8% has air conditioning. compared to 90% of the people in US and Japan. India has among the most cooling degree days in the world, more than 3,000 per year. Household ownership of the AC in India is merely 7%, that is approx 20 million, and demand is expected to increase over 1 billion by 2050. But many devices will be used a low cost and inefficient model that will only consume more energy powered by fossil fuels that will contribute to global warming. Air conditioning currently accounts about 40 to 60% of power demand in summers in the major Indian cities. India contributes to 5% of the global annual emission from ACs in 2019 and predicted to account for 25% of annual emission by 2050. So if what is like urban heat island effect? So all these parameters led me to look into urban heat island effect that major of the cities are experiencing. So as you all know, like urban heat island effect is best visualized as a dome of stagnant warm air over the heavily built up areas, and majority of the cities are around 2 degrees Celsius warmer than the rural areas, and commercial and high density residential areas are hotter by 5 to 7 degrees Celsius. So looking into the causes of UHI, there are so many causes like low albedo materials, heat loss from the street canyons caused by the obstruction of sky by the building, trees and other objects, and air pollution in the urban atmosphere, the release of anthropogenic heat, the heat source capacity by the building material, and decreased evaporation. So there are so many effects of UHI. One will be the health effect, the energy demand and impaired water quality, and air pollution and greenhouse gas emission. So I'm looking into the mitigation strategies. There are so many mitigation strategies adopted for the UHI, but more specifically, I'm looking into the green roof vegetation. Then look into the material on the surface. Then third would be the urban geometry. Coming to vegetation, I want to look into the green roof, and according to the study, like surface temperature of an individual green roof can be reduced to 15 to 45 degrees Celsius compared to conventional and non-green roof, and the nearby air temperature could be reduced to 2 to 5 degrees Celsius, and could also reach to 80% depending on the building type. And if the extensive use of green roof is undertaken in the urban areas, the air temperature at the pedestrian level could reduce to 0.5 to 1.7 degrees Celsius. If you look into the tree shadow advantage of that, the tree shadow street could reduce the air temperature between 0.9 to 2.6 degrees Celsius. The highest benefit of the shadow provided by the trees is improving local thermal comfort during daytime, and especially in the tropical and subtropical regions. And green pavement. Urban pavements are generally like made up of materials that can reach peak summer temperature of 50 to 70 degrees Celsius. The use of grass pavement or other cool materials may reduce the UHI significantly because nearly 40 to 45% of urban areas is covered by pavements. Looking into the materials, cool pavements have several advantages. They are able to keep the urban temperature lower overnight, and cool roof. Studies have shown that the expected decrease rate of urban ambient temperature varies between 0.12 and 0.K per 0.1 increase in roof albedo with a value of close to 0.2K. So to look into urban geometry, urban canyons can reduce the total energy consumption by 30% in the commercial building and 90% in the residential building. So indoor and outer temperature difference shown by a study can peak to 5.4 degrees Celsius for the unshaded building, while the tree-shaded building did not exceed 2.4 degrees Celsius. A study established that the street design influenced the thermal comfort at the pedestrian level and the global energy consumption for urban building. So if you look, now comes to the site which I've chosen, that is Bangalore, situated in India. Bangalore is located in India. It is one of the fastest growing cities, and it is a Silicon Valley of India with rapid growth in information technology, biotechnology, and manufacturing sectors. About 35% of IT force works in Bangalore, and the spatial extent of the city is increased from 226 square miles in 1949 to 286 square miles in 2020. These are some of the images just to show the how the sense of the city. So coming to the climate, the city is placed in warm, humid climate zone, and Bangalore has a tropical savanna climate with distinct wet and dry season, and it is an annual rainfall of 35.6 inch. Due to high elevation, that is 900 meters above sea level, the city usually enjoys more moderate climate throughout the year. The coolest month is January with average low temperature of 15 degrees Celsius, and the hottest month is April with a high temperature of 35 degrees Celsius. The average annual percentage of humidity is 63%, but it varies from 32% in the month of March to 87% in August and September. So if you look at the population, but in 2020, the current population is like 12.3 millions, and that is 3 to 4% of increase is happening each year. By 2031, the city will have 20.3 million. And population density is approx 6,500 people per square miles. To look into the land use, Bangalore has been experiencing unprecedented rapid urbanization and sprawl in recent times. Unrealistic land cover changes with a stringent increase of paved surface. There is a sharp decline in vegetation by 32% from 1973 to 1992. By 38% from 1992 to 2000, and by 63% from 2002 to 2009. So there is a decline of water bodies. Before there were 265 water bodies present in Bangalore, but now you can see only 98 water bodies, which most of them was encroached by the slum areas. So the environmental issues that the cities are facing are like air quality. Bangalore's air quality is worsened by 7% in 2018 compared to 2017. This puts the Bangalore at most 4 times the World Health Organization annual limit. As a result of the studies have shown a rise in blood pressure, inflammation, and heart attacks and strokes. Air pollution is a major hazard that the city has been facing, and there has been a consistent increase in vehicular population at an average rate of 8% per annum. The greenhouse gas footprint is 19.7 million tons, and the major contributor sector is transportation, that is 50%, domestic is 21%, and industrial is 12%. So, another main contributor to Bangalore's energy emission is energy use. Energy component is 60% of the total carbon footprint, with the electricity usage in residential and commercial and industrial sector contributing to about 75%. Residential building consumes 33%, and commercial and industrial, on the other hand, consumes 30% and 29% respectively. Emission from the municipal solid waste also constitute the remaining 10%. All these issues are contributing to UHI, and the city is experiencing a surface heat island effect with a temperature variation from 1 to 7 degrees Celsius within the different land cover. Additionally, as urbanized land continues to increase in areas which induces the UHI effect, increased temperature may cause an increased risk for heat-related illness and fatalities. Bangalore is getting hotter. A report by the Bangalore Climate Change Initiative says that the city's temperature would increase by 1 to 2 degrees Celsius from 2021 to 2035. So in conclusion, UHI is rapidly urbanizing in India. Additionally, mitigation strategies are required, which can help in diminishing the impacts on climate warming. In the coming year, it will be important for the city planners in areas such as Bangalore to determine why in which to maintain vegetation greeniness in order to minimize the harm to vegetation and not amplify the UHI effect. As less studies are done on analyzing how relation between the indoor climate and the physics of the building interact continuously with the outside climate. So coming to the future studies, so I narrowed down 3 sites, which is one side would be a low-rise building, and one will be low-rise and the mixture and high-rise mixture of, and one would be the compact building. All these sites have experienced the UHI effect. And I would like to analyze through the different percentage of scenarios of grass, trees, and green roof, and mixture of both. And in terms of material and cool roof and permeable reflective material for the and outputs, I will be looking into the hourly and temperature, wind speed, relative humidity, and energy used in a building using the environment model. Thank you.
Could you go to the last slide? Sorry. Okay.
Alex, are you about to say something, or should we jump in there?
I'm sorry, you can jump in. I just wanted to read this. I apologize.
Okay. No problem. Diamond, I think this is really intriguing, and obviously it's a really important and problem, and the scale of which is absolutely massive. And I think you've shown us some really good research here. Some of those charts you showed us were quite shocking and really effective. Is your kind of ultimate objective to propose kind of a set of best practices or guidelines, or the foundation of some kind of rating system or something along those lines here?
Yeah, I imagine like as this in India, there are a lot of smart cities things are going on in which Bangalore has been selected for the development. So through my findings and the research, I wanted to give those guidelines to them, like in order to like how to reduce the temperature in Bangalore with the trees as a solution.
Okay, and I think that's a great goal. And this may we go. I think maybe if you wouldn't mind going back one more slide here. Yeah, this one. I'm interested in kind of how you plotted out the scenarios here and how you're going to apply them in practice. Like, is this a study for every permutation of what we've got about 10 or so variables here, kind of controlled for modifying one at a time, or are you looking at a scenario of one item from line 1 item from line 2, and one item from line 3 that are kind of put together in some hand-picked combinations? Or how are you going to approach the study of the scenarios you're looking at?
Yeah, like this is just a numbers which I provided at the beginning, but I'm gonna look into like by doing a permutation combination and which might be the most effective according to the results which I get.
All right, I think that's a really good strategy, and I'm not sure how many sort of sub variables this ends up leading to, but to me, if you also had 3 different sites you were looking at, so that's starting to become a whole lot of different scenarios, which is great. And I don't know how involved, I've never used this software, I don't know how involved it is to set all this up. But the more systematic you could be with kind of a catalog of the different permutations, where you could go in and see, okay, if I make these assumptions about everything else, I know I would see this much improvement from going with a cool roof or a green roof, or a green roof with there are many different vegetative properties on green roofs as well, and so there's a lot of subtlety. And I think that if you set it up in a really systematic way, you can have kind of a guidebook to how to sort of mix and match these different strategies to come up with the most effective solutions, rather than just kind of somewhat arbitrarily handpicking this and this and this go together, and then this and this and this go together, where it's a little bit harder to draw real conclusions about what's driving the changes.
I was also wondering, how you would decide where those particular strategies could actually be applied. I assume, when we talked about retrofitting versus other solutions that are more difficult to implement, I guess that here we should be also talking about that, right? Or are you imagining like just covering everything with, what's your strategy about like those scenarios? And how realistic do you want to be about it? Is this related to some kind of, I don't know, a master plan for the city where you know how the city is going to be evolving and you want to tap into that? Or can you talk a little bit about that?
Yeah, right now, like I was thinking of using in existing site, which is already built up area. So in that site, how to reduce the temperature in the existing environment, which they're already experiencing the heat temperature. So
okay, so I think
kind of
so in that case, maybe it would be interesting to actually rank these different possibilities according to the feasibility that you're talking about a place that is already built up and not a place that will be built from scratch. So it might not make sense to look at some of those strategies because they're really difficult to implement. And maybe there's also a correlation between, the cost and the feasibility, and so it could help you to understand which of those strategies you might want to test first, and maybe limit them also based on some kind of a criteria like that.
Yeah, Diamond, I think I had some similar thoughts to the previous comments in terms of trying to get a sense of, I think maybe there are two things that jump out to me. One is trying to define this. I worry about this being it's very ambitious, which is great. It's something that has potentially a large impact, but also could become very difficult to get much mileage on within the scope of this remaining semester. And so part of the bigger question is like, what is the primary focus? Is the idea of mitigation of urban heat island effect, is that perhaps too broad, or could you restate your question? What's the research question again?
Yeah, mitigation of heat island effect by utilizing urban vegetation, surface cover material, by analyzing the scenario to evaluate thermal comfort and energy consumption of the building.
Okay. Concrete. Okay. So I get among these sub questions, it then begins to talk about surface or form and surface. So by talking about urban, I'm not sure what do you mean by special morphology?
Like the layout of the site.
Okay, it's like spatial.
I think you wanted to write spatial.
Spatial, yeah.
Yeah, sure. Okay.
Yeah.
So formal versus then material, which I think gets a little bit back to Dayson's point about if you could isolate those variables, and I do think a matrix is an interesting way to talk about that in terms of variation in one axis is variation in form, this morphology of density, and the other one being material choice and whether it is the white white roofing versus green roofing, and having just these variables and beginning to isolate those and see to establish what priorities there might be, because I worry about the big question being too big in terms of and actually there isn't actually even a question mark there. I'm actually trying to make a question out of that, because I think that it's almost too. I think the question is maybe something a little more specific along the lines of how much, what is the impact, or what is the exact quantitative impact of urban heat island effect? How much impact can be made, how much mitigation can be made by utilizing urban vegetation? which then starts to get down to those sub questions of, well, in what ways, what are the variables that could be manipulated? What are the different levers that could be turned that could do that? And to what degree are they actually making that difference? My other question then is similar to my question to Maite, because obviously there's some overlap between what you're doing and Maite's overdoing. And I would suggest you do both coordinate a bit and maybe share some of your resources and share some of your test results, like as you two are both experimenting using this software to coordinate. But I have a similar question in terms of the spatial component. If you imagine this staying more at the scale of thinking about this in terms of neighborhood planning, urban analysis in these blocks, and or if you imagine getting into the scale, to human scale, to demonstrate or show before and after scenarios in terms of atmospherics or perception. Well, I'll just pose that as a question to you. Okay, what in terms of your output, do you imagine it staying at that larger scale, or do you imagine also pairing it with a spatial component?
Yeah, I thought like first I'll start with urban scale, and then if time permits, and I'll look into the smaller scale, like selecting each of the one buildings in that area and what inputs which I get from the urban parameters of that, and apply it to the smaller one building of each site and see how does it affecting if I get a time to do that.
Well, I think the way you've answered that suggests the priority. Obviously, it's like if that spatial component is clearly something that is a bonus, but it's not the more critical part of this. It doesn't define the project. That begins to answer the question, and part of that makes some sense in terms of just the viability. Are you in the U.S. right now?
Yeah.
Yeah. So the viability of being able to, with Maite's project, we were talking about the potential to go on site, do some field experiments. Obviously, that's out of the question for you. But then even being able to accurately 3D model a subcomponent of this is a little bit more of a challenge. And obviously, with Google Earth data and different things, there are ways that you could begin to do that that Maite could more readily do. I think it comes back to somehow refining this larger question, and then therefore the methodology in terms of what the impact is. And if it is all about simply trying to find ways to find an optimum ratio of, what's the critical ratio of change that needs to happen in terms of these surfaces and these different considerations that makes a difference, regardless of form, potentially, regardless of spatial experience, regardless of all those types of things. In other words, one could argue that on a given block, you could make it might make more difference to make one change and concentrate all of that to one portion of the block, which then makes a larger net difference in terms of urban heat island effect, but might not enhance the experience for 3/4 of the block. Does that make sense? This is just an example of thinking about the application of this. And if the priority is ultimately just to move the needle in terms of temperature change, without balancing it from the bottom up in terms of the experiential aspect, that's one way to go about it, as opposed to having that pressure from beneath in terms of thinking, well, you want to somewhat democratically distribute the greenery or these other surfaces across for the experience of people, even if that's not quite as effective or efficient in terms of changing the urban heat island effect. I'm just bringing this up. I'm not giving you an answer here, but I'm rather just suggesting that those could very much influence the way that you structure your focus and the way that you explain this and the way that you arrive at a conclusion from this.
Yeah, I need to think like, it's a very vast scale. I need to narrow it down a little bit. And I was thinking like this could help in like future planning for the urban development in the city of Bangalore, which they could use and utilize it for further.
One thing, again, I'm piling up on what Matt's saying. Maybe I should just stop talking. But Matt's, I mean, the way I think about this problem is it is way too many parameters. And the simple way, the suggestion that I think most of us are trying to say is, kind of like pick your favorite, but make an educated guess of what you want to pick, and try to understand that effect really, really well, rather than trying to understand the effect of 20 things in a mediocre way. That's really the way to think about this. And to make the educated guess, you may want to look at other places with similar city types, similar climates, similar effects, and where things may have been already implemented or not. I mean, you're obviously not the first one looking at these things, right? So there must be precedents where people have evaluated and they said, oh, well, painting the roofs white has a 500 times bigger effect than putting trees in the street, right? And that gives you an idea. Okay, let's look at white roofs then, and then let's put trees later on that list. And then if you have more time, you can put the trees back. But you want to find out in a smart, educated way which of those 2 or 3 are interesting and doable in your software too, and then take it from there. I think that's how I would look at that.
I wanted to also add, I agree with that. I think you should look at some precedents. I mean, I know that Los Angeles is already testing that, painting streets white, and so you could really pick some cities that are doing that and look at that, so that you just don't redo work, right? And the other thing is that when I look at your questions, what Matt was talking about, I think that your main question or here statement, it could probably be simplified. Right now, it's almost like you're asking a second-degree question. And the first question is like, how is the temperature going to change? Before you can even start talking about energy consumption, because that's incredibly related to, not just spatial morphologies, but occupancy and all sorts of other things that are probably not even accessible to you at that scale. It's really an enormous amount of data that you would probably have to handle to understand how what you're going to be testing impacts energy consumption, not to mention comfort, that is even more subjective, right? So maybe you could kind of scale down your ambition and say, well, I'm just going to try to figure out first what's the impact on the temperature. And then, if you're interested in the impact of the morphology, that's really complex, because you would probably have to somehow create really similar conditions in different types of morphological, arrangements, let's say, and compare that. But what you're going to be comparing, like when you have the same amount of surface exposed but organized differently in 3 dimensions, like what would those exact things to compare be? And that's really difficult if you start really thinking about it. The materials might be easier, but yeah. So simplifying and clarifying, I think, would really help.
Yes, I agree. This is a very important topic, and I applaud you for looking into it. I was really impressed by your findings about the increase in air conditioning use into the future, the increase in temperatures and the population and CO2 emissions coming from India in the future. So it's major what you're looking at, and I understand the tendency to want to find the ultimate combination of solutions to have the most impact. So one thing that I really found my personal interest in what Diamond is doing is that she always said she wants to have a major impact for her country. So I think that's a very noble goal to have. It could be, this software is very powerful that Diamond discovered and that she and Maite are going to troubleshoot together. It can do building level, it can do urban level. And the reason they chose it was because they both had a common interest early on in looking into the impacts of vegetation, which other software packages couldn't look at. So I think, white roofs and other kinds of material properties, other packages could handle, but the wind through the different morphologies combined with the vegetation was something that originally motivated Diamond to seek out this software, which they were successful in getting a grant to purchase. So I wonder if going back to that original and just looking at one thing, and then if you get a chance to add on other solutions and then compare them one at a time, and also looking at how they differ on each different block. So you showed 3 different blocks, and try each strategy one at a time on each one. That could be a way to, which I think you discussed in our meetings, you wanted to separate things, but the way you're presenting it makes it look like you just want to try it all at the same time and compare it to the baseline, which in itself, if you can manage it, would be interesting. But I think what we're after is wondering which one of those, in case they could only choose one, would be the most impactful. And I think you can figure that out. Also, like Dr. Nagy said, by doing or continuing to do a literature review. I know you all have been, I've purposely held you in the literature review stage quite a long time this semester to see what's out there. And you're probably already getting a sense of what is having a bigger influence. One thing unique about Bangalore that you showed, could you go back to your temperature slide? Unique when I compared to Austin, I mean, where you showed the nighttime and daytime temperatures. So that's a pretty big difference, isn't it? If we look at April or compare, like in the daytime versus the nighttime. So I'm thinking you could do some kind of night cooling situation in some of the taller buildings. Not to add another variable, but it is a unique situation that we don't have here in Austin. So I agree with the other input that you might want to try to find exactly this climate and look and see what other solutions have been found. But also look for getting in contact with professors in this region and see what they're looking at. I know you tried to reach out earlier, but to get some feedback from people working in exactly this city would be useful.
Yeah.
One thing I've noticed, Diamond, and if you go to the first location image, actually the one where you're showing kind of an aerial of Bangalore, 2 slides, slide 22, right? It occurs to me that there obviously are some areas that are a lot greener than other areas already within the city. And I'm not sure what your access would be to determine, energy consumption within or temperature, relative temperature points in different parts of the city. But you could imagine that being able to speculate a bit by seeing a difference already. I would just imagine if your general hypothesis is correct and what we generally understand about urban heat island effect, I think one would expect there would be some fairly different microclimates within this city already. That I would just say that I'm not sure how far you could get with that, but that might already start to set up the argument. But I'm just thinking that this builds upon a lot of what's been said. But if you were to distill this down to, for example, being able to explain the value of one tree in this city, and I'm just thinking of, as an example, I was walking a project site once, and we were looking at different ways to try to adapt a given structure and to do some adaptive reuse of a building on a given site. And I recall that the strategy to work around a given tree on the site was the foundation would need to be modified, and it would cost on the order of, let's say, $20,000 more, as I recall. Not a not insignificant amount. But the arborist said that tree that we were preserving was worth $200,000. And in relative terms, it was these opportunity cost elements. It's like, you're spending $20,000 more of actual real money, but you're not gaining $200,000, but you're preserving an asset worth $200,000. And you're almost trying to do the reverse. You're trying to introduce greenery, introduce softer surfaces, lighter surfaces. And if you were to be able to quantify it, not necessarily in those exact terms, but maybe it is to do with in some incremental amount of temperature difference. It's 0.01 degrees per tree in terms of a microclimate temperature. If you were somehow able to bring it down to something tangible to the layperson, if your goal is ultimately to have a broader impact rather than just to be in a discussion in this type of circle, it needs to somehow be something in terms that can begin to make a difference either monetarily or in a very specific way to larger audiences. And I don't have a direct means or methods to get you there exactly, but I'm just suggesting that rather than if your conclusion at the end is yes, urban heat island effect, I've confirmed it still is a problem, and it does help to introduce other strategies. It might be too vague to become applicable and tangible and then actionable for the individual and either in their own unit or then code-wise, as you mentioned, to do with future development or future policy that comes into play. So you might think about, not only for the sake of just your own clarity and sharpening this down to a point, but for the sake of communicating to others and larger audiences, how you can quantify this and make it meaningful on their own terms, if that makes sense.
Yeah, definitely. I'll think about this more and scaling it down to like one part.
Are you in touch with the city, maybe planning department, or that could be also an interesting thing? You know, one thing is the academics, but that could help you understand what is actually being done or what the plans are, if any.
Yeah, I thought of contacting the department for the building heights and the planning for that. I can, if I get hold of them, I can like talk more about the city planning.
Yeah.
Yeah, definitely. I think they would be interested in your results, Diamond. So that's definitely good advice.
All right, any other comments on Diamond's presentation? Even from students? Students are welcome to chime in. We have a couple of minutes here. All right. Well, thank you, Diamond.
Thank you.
Conclude there. And I suggest that we just keep, rather than taking a break and rejoining, we just move through, if that's okay with everyone. And thanks, Zoltan. I just saw you sign off. Thanks, Zoltan, for joining.
Thank you. I have to jump off the next meeting. I'm sorry. Bye-bye.
Right. So Robert, whenever you're ready, you can go ahead and share.
Are you seeing the slideshow?
Yep, can see it. Okay.
Not sure why it's taking so long. Okay, thank you. And I enjoy listening to all the past presentations. So minimize good. My thesis is the comparison of two architectural intervention strategies for climate resilience, floor to ceiling height and overhang depth, with my advisors being Dr. Felkner and Professor Michael Garrison. Professor Garrison. Oh. The research question for my project is, what impact will climate change have on the cooling energy use and cooling loads for mid-rise office buildings in Austin, Texas, when designed with reduced ceiling height compared to adding window overhangs? This research question shifted substantially from the Thesis A presentation I made, and I will touch on that briefly as I go through my methodology. Because, so I came into the School of Architecture from a mathematics background, having very little architectural experience, and I had a lot to explore and catch up on. So my original passion was to learn how to design from scratch a fully self-sustaining building that requires no outside resources to provide resources for its inhabitants outside of emergencies, whether it's a comfortable temperature, it's food, it's water, it's electricity. That was the original desire, but then I realized that I don't have the experience nor resources to be able to go such a far leap. So I shifted to eventually to analyzing the reuse of waste. And although this fascinated me a lot, I shifted away because I found that there are already companies that like buy building or building block companies that build Wastecrete, which I was interested in designing for businesses to use. And I was less interested in analyzing the success of companies. I was more interested in actually creating my own Wastecrete, but since it already existed, that disincentivized me from pursuing it. So that shifted me to looking into building resilience code, which eventually shifted me into what the current topic is. So I realized I had to focus down because my ideas were always so broad and far-ranging for such a long time that I needed to narrow my scope to a very focused topic to be able to come up with a thesis that is substantial and meaningful. So the next steps were to select the design intervention strategies, and I chose to look at the lowering the ceiling height and adding overhangs because I was very curious. I was looking around the, at least for the residential building I'm in right now, the ceiling height is 8 feet. More commonly in office buildings, I read that it's 9 feet, even though 8 feet minimum for bathrooms, 7 foot 6 inches. But I was curious, how much energy would it save if you just lowered the volume of the space? Not focusing on the building height itself, because I saw a lot of literature that compared the building height. But what if we lower, instead of reducing the number of floors, what if we reduce the ceiling height of each floor? And then the next step was, since I wanted to address how energy efficient buildings will be across changing climate conditions, I was able to access climate change weather files from the IPCC. And then I needed to select building typology. And the building typology was influenced, I chose it after meeting with the Austin Energy Green Building team and Sarah Talkington's team. And their advice, I was asking them which building would they recommend I analyze, more specifically, which would be most useful for the city of Austin. And they stated, just look at mid-rise office building. And that's the building I decided to model in eQuest. And I realized that the Austin code is based on the 2015 IECC code. So that's the code I used when I designed my eQuest model. And the reason I chose the overhang, and I went over the reason I chose overhang and ceiling height factors, but there were many other building characteristics I could have analyzed. And when I was, before I narrowed down, I wanted to model a building, like a building information systems model, where I modeled all of these different factors, but I realized that would result in over 19,000 different scenarios I had to model, and I was not equipped or experienced enough to do an accurate enough model for all these different factors. So when I built the simulation, I decided using the inputs from the IECC and IPCC and eQuest, I modeled this building here. It's a 4-story mid-rise office building. And the reason the indented white space is the eQuest's default visualization of any building above 3 stories, the middle stories above the mid stories above the second story up to the final story are depicted as a white space. So if it was a 5-story, 6-story building, there would still be a white space in there. and I tested out different building number of building levels, and the white space just it looks a little larger. But that's how they represent building with more levels than 3. These are the parameters I changed. So I kept at 10,000 square foot footprint, and then 4 stories with 40,000 square feet total. And this was the default window wall ratio that eQuest generated, and constant window sizes. So the variables I changed were the overhang, as you can see here, 3-foot overhang, and the ceiling height. In these visual images, you don't see the ceiling window from floor to ceiling, and it's that this space here where my cursor is represents the plenum space, and I kept the plenum space at a constant 4 feet. That was the default settings for eQuest, so I kept them constant at that for the mid-rise office buildings. So the results from these simulations, I focus on 2 particular reports: the building HVAC load summary and the electric consumption. This is I'm not expecting you to read this. I'll show you the graphs in a moment. These are the reports generated from the electric consumption. And what you'll notice is that this is just a selection from one of them, that the space cooling is the most intensive, and then the miscellaneous equipment is the next most intensive, and then the area lighting. So these are the 3 I focused on the most to compare. And these are some of the graphs, the results. And what you see on the left, it's difficult. I'm comparing the baseline, and the baseline model was a 9-foot tall floor to ceiling level with 0-foot overhangs, to still a 9-foot tall ceiling with a 3-foot overhang, and then an 8-foot tall ceiling with a 0-foot overhang. As expected, an electric consumption, this graph up here shows the total electric consumption from the electric consumption chart. It goes up from 2020, 2050, 2100, but it's very difficult visually to tell the difference between these two, which is why this chart on the right here shows the marginal differences in here. And this is important because I expected, my hypothesis was that reducing the ceiling height or adding an overhang would have a much larger reduction on the energy use than it shows here. But here it shows just less than 10 megawatt hours for an annual reduction. And it shows it's very similar, which is interesting, is that even though in 2020 and 2100, the 3-foot overhang outperformed the 1-foot ceiling reduction in energy savings, in 2050, they're nearly identical, and actually reducing the ceiling height reduced more energy than adding the overhang. And then down here, these lower 2 graphs focus on the cooling energy, the amount for space cooling. And it has a similar pattern as for the entire electric consumption and for the percentage as well, except there's a greater differential in terms of the percentage here. But what you look down here is the percent difference is so minor. I was expecting it to be a much greater difference, especially because I did not assume there'd be a direct linear relationship, but if you lower the ceiling height at 1 foot from a 9-foot to an 8-foot, that's an 11% reduction in volumetric space. And I expected that to have a greater impact on the amount of energy needed to cool and for electricity. This is another chart, which another way of visualizing the amount of energy used. And this focused on the 3 categories that took up the most energy for the buildings in the model. And these are the numbers representing what this is showing visually. And the colors represent the decades being modeled. And as you can see on the right side of the graph, you only see a orangish color. That's because it turns out for lighting and miscellaneous equipment, the energy use across all decades remained the same. They were unchanging regardless of the climate conditions, the weather outside. But as is evident, that for the cooling in 2020, the energy use looks almost identical to the lighting and slightly less than the miscellaneous equipment. And the numbers are supported here. So for lighting, the cooling is, in 2020, for example, when these are the 3 different scenarios that were modeled, it was between the lighting scenario and the miscellaneous equipment scenario. But it used more energy than both of them in 2050. So this is suggesting that right now, miscellaneous equipment, that's powered equipment outside of the lighting equipment that's required. Miscellaneous equipment requires more energy for this modeled mid-rise office building. But by 2050, cooling is going to surpass that energy required. And by 2100, it's going to get far more severe, the need for cooling, the energy use. And then the other report analyzed was the HVAC loading summary. And this looked at, it showed a monthly breakdown, and it shows the cooling energy, the maximum cooling load, the heating energy, the heating load, and same with electrical energy and maximum electrical load.
Jesus.
From these results, I looked at the heating energy right here. And this was showing the amount of energy reduced, and this may be flipped in your mind, but the 1 foot ceiling height reduction reduced almost 10 MBTUs in 2020, and it's slightly less. This is in comparison to the baseline. So this is how much more energy is reduced for the to heat the room. Whereas the 3 foot overhang, as is intuitive, increase the amount of energy, to heat the room. And that's my intuition for that, is that during the winter time, the overhang blocks the solar radiation gain. So the heating for the space needs to go up that normally would not occur if there is no overhang. And then for the cooling energy, a different phenomenon occurs, is that the 3 foot overhang outperforms the 1 foot ceiling height reduction by a substantial amount in 2050 compared to the other 2. And this is an interesting phenomenon in the model scenarios, is that I would expect that there to be a continuous increase in or decrease in the amount of energy used or power used from 2020 to 2100, except 2050 was an anomaly in the amount that it didn't change or did change, and that needs more investigation. This was an interesting result that needs to be looked into some more, because even though the 3 foot overhang uses less energy than the 1 foot reduction in ceiling height, it requires the strategy by reducing 1 foot ceiling height needs a less cooling capacity. It can, the cooling capacity needed, the power of the cooling unit, the chilling unit, can be less than the power needed for the adding the 3 foot overhang. And interestingly, in 2050, more power than, this is the 0 line here is the baseline. This represents the amount of power needed by the baseline model. And the amount of power needed for in 2050 for the 3 foot overhang was greater than the baseline. Whereas for all 3 scenarios, the power for the 1 foot ceiling height reduction was less. And that's an interesting inverse of less energy is needed for when using a 3 foot overhang design intervention strategy, but less power is needed for the 1 foot ceiling height reduction. So my conclusions from this are that yes, the 3 foot overhang strategy does save more energy for cooling overall, but the energy savings are not as substantial as I hypothesized. I thought they would save substantially more, especially the ceiling height reduction with regards to reducing the volumetric space by 11% or so. And I think further research, I need to do a life cycle assessment and focus particularly on embodied energy, because if a reduction in ceiling height requires less material if you're reducing the ceiling height, and you need a smaller chilling system, then the embodied energy
would be less intuitively, it's less for these strategy to reduce ceiling height. And as embodied energy becomes more important in the future, as we get more efficient systems, mechanical systems, I can imagine that the strategy for reducing ceiling height would become more favorable and through a holistic embodied energy perspective. And then the last step is more of the energy savings need to be matched with the economic cost savings. And I will return back to the conclusions slide in a moment. I would like to thank Dr. Faulkner for her guidance in helping me learn how to focus on just one narrow topic rather than bounce around between all these different areas, and Professor Garrison for his support as well when I was asking the questions, and Adam Pirik for helping me understand the fundamentals of eQuest so I can model it using the schematic design wizard. And more thorough research, in-depth research can be done and will be done using the design development wizard and the energy efficiency measure wizard that is within eQuest. I would also like to thank Sarah Talkington's teams for helping me decide the building typology, and our fellow student Ben Marshall for I was looking for the IPCC weather data and he said he had it, so that helped me be able to model it correctly, the climate change impact. And then these, all of these references were for my evolution of the anthroarium proposal to what I've been presenting to you now, and including the librarian, Professor Ficus, for the building code resilience of Sutton Hall. Going back to the conclusions and further research, that this narrow research did state what may have been intuitive to a lot of you, and it did support that a 3-foot overhang strategy does save more energy for cooling than a 1-foot reduction in ceiling height. But a more in-depth study could compare different reductions in ceiling heights, just focusing on energy use or power use, and changing and adding, looking at 1-foot overhang to a 2-foot to a 3-foot to a 4-foot, and then changing. A more comprehensive study would change all the different parameters, whether it's the U factor, the R factor, the R value, the solar heat gain coefficient, window wall ratio, etc. But this is what I have as of now, and I'd gladly welcome critique and advice on what an intuitive next step would be for this research.
Thank you, Robert. I want to make the point Robert did go back and forth with many different research ideas, and that's a testament to his genuine curiosity and interest in coming into architecture as a non-architect. So it was refreshing to see his point of view about things, and his creativity definitely was inspiring. I do think with the eQuest, it's a new software that Robert just learned this semester. Is that right, Robert?
Yes, I was learning.
So yeah, maybe it's going to be the case that you would want to rerun some of the simulations and troubleshoot it a little bit, or even look at comparing it against a different software. I do have questions about the 2050 anomaly. I think that's a mistake somewhere in either the software or, it's just not, it's not making sense to me that your cooling loads would go up with an overhang. Like, I can't imagine any case where that would happen. I'm also not sure about only a 0.6% reduction in cooling loads for a full foot difference of ceiling height. I like the approach of comparing two different strategies to try to see where you can get the most bang for your buck. And I do think looking into window wall ratio in the future could be a good one, especially for some place like Austin. But I would rerun some of these calculations. I know you were planning to anyway. And I do think your conclusion is interesting that yes, while a 3-foot overhang now might make sense with considering our operational energy and our power source, in the future, once we're using more renewables, it might use more embodied energy than it's worth to save that operational energy. So in that case, lowering your ceiling heights, you might see a switch in the future, which is your better strategy. And that's a very interesting point that you make, looking into the climate in the future and trying to gauge which would be your best strategy. Embodied energy, as you mentioned rightly, should not be discounted. But I'll open it up to the others. Thank you for your presentation.
Robert, I don't quite understand some of the units. I'm wondering if there's when you were using megawatts, I'm wondering if that should be kilowatts. There's, just to understand the scale, Austin only uses 3,000 megawatts for the whole city. One coal plant is 400 megawatts. So, I'm looking at those numbers and I'm saying, and when you're looking at 1,000 BTUs, a million BTUs even, I think when you convert those over, you'll get kilowatts, not megawatts. So please check that. I think that might be a typo kind of thing in here, or maybe I'm just not understanding then the relative units there. But that's the only one thing technically. I do want to get into something else. That is software engineering, and in some ways architectural engineering suffers from tunnel vision. And while you've been focusing, which I think is fantastic, and you've gotten, I think, some really important information that I think people would like to know, you have to understand that an architect makes hundreds of decisions based on balance, and if not 1,000 decisions. So for instance, we used to use 12-foot ceilings in Louisiana because buildings were not air conditioned and we let heat stratify, and we had double hung windows, so we'd lower the upper sash on the leeward side of the building. Buildings used to be, they used to have a taller ceiling. When we started air conditioning buildings, we made smaller volumes because we thought that would be less air to air condition. The trend now is, I think the standard in Austin are going to be 9-foot ceilings. I think they're going to 10. And it has everything to do with other issues that we're imbalancing. So when we look at, when I'm looking at just how much more air I'm having to buy air condition, or how much more material, I'm trading that off with daylighting. How does that improve the daylighting? How does that improve the, whether I'm using displacement air conditioning, whether I'm using radiant systems, which don't rely on the air system. So there's many, many things that I'm trading off. I think you need a chapter at the end or something that begins to really understand that while you're focusing in on something, that you understand that's just adding more information, but it's very dangerous then to draw some kinds of conclusions that it would be better to have this overhang at this distance, or reduce the ceiling to this distance, without understanding how other items are coming into play. Daylighting, radiant heating and cooling, displacement conditioning, those kinds of things. And so, give you an example of this. We had someone who was a very bright computer modeler showed us a project once that had to deal with embodied energy. And they were very proud of a project they did in Japan, where they actually proposed doing away with, or did away with, a concrete foundation and used creosote because it was wooden. And what they didn't understand was that the creosote has off-gases something that's really harmful to interior health. So they made an interior environment that was very, very unhealthy. And that's just one of the decisions that we trade off when we look at materials, or we look at something, in terms of the decision making that we're doing here. So yes, focus, but don't make the conclusion so then all-knowing that you don't understand that there are other issues that may vary overhang and ceiling height that will change things a lot. And you may change the opacity of the window or the dynamics of the space in terms of light shelves and the way that light's transferred into the space, other things like that. There are all those decisions we have to balance. So again, I think you need to check your units. And I think that doesn't necessarily mean that the analysis is wrong. I just think there may be a misnomer about the units.
Thank you on that. I did check the units, and I was surprised as well, because I did originally think they were kilowatt hours, but I equest whenever the units are small. I'll go back up to the equest slide. Even though it says it's kilowatt hours, in the top left it says whenever you see the times 000, that means you would multiply this amount by 1,000.
Yeah, I think you got.
So that's what I understood it to mean. That was
the K is 1,000. So again, I think this is I think you got a unit problem still.
Okay, I'll look into that in more depth.
Yeah, you definitely do. So I would definitely check that. And yeah, thank you for those points. You did look a little bit about, we talked about daylighting being hampered to some extent by the overhangs, and how much would that electricity amount trade-off be with your cooling. But then you didn't go into the human comfort or psychology of lighting. It would have been too much, but it's worth mentioning in any case that this could be a trade-off to consider. Also, one thing we didn't consider in your work, or you didn't have time to look at, is the ceiling height, lowering the ceiling height. A little bit of discussion about the implications of that in an overheating scenario, being possibly, while short-term reducing your energy load potentially, could also make a more dangerous situation if you lost power, if you're not able to cool that space with air conditioning. So then you'd want to balance that risk against, what if we did still have 12-foot ceilings and we could better endure high heat extremes without air conditioning for a longer period of time if needed. So maybe that could be in your discussion, but more urgently, I would rework these units and try to go to that anomaly situation. And overall, I think you'll see more energy savings for both strategies than what you found. But the point being, what Professor Garrison said, it's important to consider the holistic decision-making process, or at least mention that in your discussion.
I will make sure to mention that, and I'll rerun the models. I was pretty confident because I've run it many different times, and I'll go double check because I can understand how the numbers may not sit well with your experience. So I'll rerun that.
Yeah, I mean, get another meeting with Adam as well. It's a pity we don't have him here right now, do we? If he's the one you were talking with, but
he would have been.
Yeah, double check.
And I was wondering whether any of you outside of Adam had experience using the eQuest modeling software.
I use it all the time in my class.
You do use it?
Okay. Yeah.
Okay. I think that's
What you mentioned that that it was your meeting with Austin Energy that led you to choose the mid-rise office building type.
Yes.
What was the logic behind their suggestion of using that building?
Well, it was one of the members, I forget his name. He just, I wouldn't really say he gave me some strong logic. He just offhand said, a mid-rise office building seems like a standard, useful building model that would be useful to Austin, but he didn't, I did not ask in more depth why he recommended that, unfortunately.
Okay.
But that was just his statement.
so that choice had a really profound impact on your findings. It's clear here from your results.
Yes.
And it's a totally valid choice. I mean, you could choose it. You could choose to study anything. So there's nothing wrong with it. You know, it's not in Austin, I wouldn't say really a dominant building type, although there are plenty of them here. But your results make it clear that your building is heavily internally load dominated. And what that means is that it's not that there is any less heat transfer, you know, per square foot of building envelope than in the other building. It's just that the internal loads are so much larger compared to the relatively small surface area that's enclosing the volume, that you don't see, you know, the kind of big impact that, you know, we as architects would hope to see generally by doing things like adding shading devices and changing the ceiling height and so forth. And you know, the reason that your lighting and your plug loads aren't changing is because the only thing that those would potentially respond to in a, you know, climate scenario would be changes in daylighting availability. But without considering that, those things are just running on a schedule. So they're going to run on the exact same schedule no matter what the weather is.
Jason, though, it might make a difference if they're LED or if the lighting was switched out to be LED versus whatever base model you're using. I assume it's not LED.
No, absolutely. Yeah.
Then the envelope's going to become more important.
The lower the internal loads get, the more important the envelope becomes. Absolutely. And so, you know, in the absence of having, but even on a very large building like that, it's hard to optimize those internal loads to the point where the envelope becomes, you know, dominant, but it certainly becomes more so. So that's one thing. And the change in ceiling height is related to the same factor. The reason that you're not seeing very much change there is because you didn't change the size of the windows. So, you know, for each floor level, it's like think of it like a big pancake. You're just making the pancake a tiny bit taller or a tiny bit shorter. You're not changing the surface area that much on the exterior. Plus, it's solid wall, which you get, you know, relatively minor heat transfer through compared to a window in already an internally load dominated building. So you couldn't. There's no reason to expect to see much change from that, in my opinion. So, you know, I think your conclusions, assuming, you know, the other questions that have been brought up, you know, are answerable. Your conclusions, I think, are valid for this building type. I wouldn't, though, necessarily extrapolate them to, like, compared to a single family house, say, because it's a completely different animal.
Yes.
And, you know, there, a change in the height is going to make a much more significant difference in the surface area of the building, and therefore the amount of heat transfer through the envelope. It's going to be skin load dominated, so you're going to have more impact from shading and so on. And one thing in particular to remember about shading, if this is a model of your shading device, it appeared the width of your windows and your windows were fairly narrow. You know, remember that's only the time, you know, when the azimuth of the sun is normal to the window that this shading device is going to have its full impact. And at all other times, you're going to get a lot of end around shading, which on a narrow, tall window, that becomes really significant. And so the change in depth here isn't going to block the sun. It's probably hard to see on my screen here, but it's not going to really block the sun that's coming in beside here anyway. It'll just extend the length of that shadow a little bit. But a lot of times that length will be going all the way past the window onto the side of the building and isn't really shading the window for many hours of the day.
Okay.
So also, I think those other things I just mentioned are still true, but you would see a fairly significant difference in the impact of the shading if you had one long window that had one long overhang, where the end around is just a tiny portion of it, versus these tall, narrow windows where the end around is like constantly impacting a major fraction of the window.
Yeah, that was hard to see, Robert. I couldn't read from the images you showed. This is where a section or, a plan, some architectural drawings would have helped. Because when I heard overhang, I assumed you were doing a full overhang across the whole floor. Are you doing just individual? Did you change it to just over the windows?
As is visible in this image, yes, the overhang is just over the windows because
it's just very hard to see. It's very blurry and small. So I can see it now, but yeah, that would make a difference. So it's not a total floor overhang. It's just over each individual window. Then that's not doing very much. I would like to see if you made that continuous, the impact that would have.
You can actually, if you considered this a solar view, this view you're showing us right now, you can kind of, visually estimate the impact here. Just imagine drawing a straight line at the edge of all that darker blue and how much more of the lighter blue you'd be covering.
Yeah.
Compared to what we're covering right now.
That makes a lot of sense. Although you said that the lighting, internal lighting will not change if there's the daylighting doesn't change, but I would assume that the overhangs, I assumed that the overhangs would reduce the amount of daylighting, so the internal lighting load would have to go up, would have to increase, but that did not change.
Were you modeling for daylighting?
I presume I must not have if it did not change in the eQuest. So
yeah, you would have to set that up specifically, and Michael may know offhand. I don't remember now what eQuest will do with daylighting.
It's not a daylight modeling software.
Okay.
You can do it though, but you'd have to use another software like Ecotech or Radiance.
Understood.
Yeah, I would almost want to have students in environmental controls next semester rerun these results in Rhino and Grasshopper and Diva or some other software and just compare, because I wonder if we would still get similar results or if it would be also for the units, just so we could understand more what's happening. But now I see your 3-foot overhangs are just above the windows. That's going to make very little difference.
I would appreciate that, and I am more than happy to run this in my free time, just to ensure that the results I got were will fix the obvious inaccuracies to you all, because that's not no wonder there's a few confusing moments, because there's just a few surprising moments. But is the intuitive to you that the 1 foot reduction in ceiling height reduces the power more, whereas the 3-foot overhang reduces the energy more? That was a surprising result for me, that the power is reduced more for reducing the ceiling height, but the energy use is more for the overhang. And that seemed to contradict itself, even though it was from the exact same simulation.
So you looked at cooling, heating, and lighting, or well, your electrical would mainly be lighting, right? So
this is the cooling power, and even putting aside the 2050 scenario, there was less cooling power. So this represents how much less cooling power is needed in the 1 foot ceiling height versus the 3-foot ceiling height compared to the baseline, which is the horizontal line. Whereas the cooling energy required, the 3-foot overhang reduced the cooling energy far more than the 1 foot ceiling height reduction. And I would assume that power, load, and energy would be hand in hand, but they did not.
I'm surprised to see that as well, and the extent of that is surprising. I mean, it does seem like if anything, it would be the reverse. Although I wouldn't expect to personally see a big difference, in the proportions between those. Is it possible? I think my recollection is there's something weird about the way eQuest reports cooling. I think it reports it as negative. Could you have a sign problem here? Could it be that bar is actually supposed to flip in the other direction?
It could be a sign problem, but it would still the positive blue bar would end up being negative in that case. But yes,
maybe just on that one. Could it be that that one blue bar that's sticking up should really be sticking down, but everything else should be as well?
No, I was carefully measuring that, and that one, that was the biggest surprise to me. That one is sticking up because I looked at it in relative to all other values, and it was the opposite direction.
Oh, that's interesting. I don't have a good answer for that, but I do have a question about, do you have any hypothesis on the kind of general anomaly between 2050 and 2100?
I've been thinking of that for a while now, and so 21. So it looks like the I haven't come up with a confident hypothesis on it because I don't know enough yet about. I just know that it will get much hotter in 2100. I know from this researcher from Texas Tech. I'm forgetting her name. She did a project for the city of Austin where she projected the temperature in the future for 2050 and 2100. And it is going to get much hotter with the humidity staying relatively the same. And the rain fall is going to become more concentrated, but the amount of rain is relatively the same.
Wait, rainfall more concentrated between 2050 and 2100?
No, sorry. The amount of rain we're getting now up to 2100 won't increase severely, but it'll be flash floods. The rate of flash floods will increase because the rain will be concentrated in shorter bursts, is what I remember reading. That it's going to lead to more severe rainstorms, but the amount of rainfall, the volume of rain won't increase substantially. Is I think what I would have to bring up the research.
One possible hypothesis could be correct or not. You just have to look at the weather files that you're using. Is that potentially the prediction is between now and 2050, it gets hotter and also sunnier, or more solar radiation. And between 2050 and 2100, it continues to get hotter, but also cloudier. So the shading does less.
That's a sensible, yeah, but I use the raw IPCC weather files, so I have not extracted them into human readable, I have not examined the cloud cover and the solar radiation from them. So that would be the next step for that. You're right.
Well, I think any intervention strategies, as you get hotter into 2100, you may see less of a percentage impact, but maybe more overall savings if you just look at the raw numbers. But it could just be that, there are other factors. There's heat coming in through your roof and, just atmospheric temperatures that no matter what you do, you're going to have a hard time saving energy in the future with climate change.
That's a good point. So other than the very useful feedback you've given me to make sure that my results are correct and check them, any other strong recommendations you have?
Robert, thanks for the presentation. And I also wanted to commend you for, I do understand, as Dr. Felkner mentioned in the beginning, I know that you've explored a lot of different things, and I commend you for funneling this down into something that could be a very specific conversation. So we could have this conversation about things such as the units that are included. So I think that's to your credit, and I know it comes from a place of you just really wanting to make a positive difference. And that's why it was hard for you to finally commit. And so this being the case of committing down or funneling down and committing to this, I have a few thoughts that are related at least somewhat to what some of the reviewers said, but also I think are a bit different as well. One of them, it has to do with if you see this as a way to, so even though you're showing that the ultimate delta in savings might be relatively small with either of these applications, with the shading devices, with the overhangs, or with the ceiling height, if that you're imagining that would just continue on a proportional trajectory. So for example, the difference between 8-foot ceilings and 9-foot ceilings, to Dayson's point, proportion does matter in terms of that you've chosen a very squat building where you have a lot of volume relative to the surface area. But are you imagining that you would be able to project that out to say now if the ceiling were to increase incrementally foot by foot by foot, they would just continue that trajectory? Or do you imagine that there's an asymptote that it reaches where it sort of levels out? Obviously I'm asked the question, but there's also a suggestion that if you have the rest of the formula built out, if there's a way that you could begin to show a few other instances that start to develop a curve potential. I imagine that it's probably a curve rather than a complete straight trajectory. So I'll let you respond to that first before I have some more thoughts as well. Go ahead.
Yes, I am expecting more of a logarithmic curve, because and definitely not linear, because just increasing, if all you're doing is increasing the ceiling height, the volumetric increase isn't going to relate to it's not going to be a linear increase to a cooling or decrease in whatever the change in load. I'm strongly guessing that because the percent change is, so if I'm changing from a 10-foot ceiling height to 11-foot ceiling height, the ceiling height changed by 10%. But if I change from 11-foot to 12-foot, it's less than 10%. And as you get higher and higher, the volume changes less. So you're right that there's many more factors influencing the energy used than just the air, the volume of the air. But my theory was that if you just change the volumetric space, yes, it will be more of a logarithmic. Maybe it's not logarithmic, but it's a decrease. Right.
It tapers somehow, yeah. So it's not linear. There's one thing that comes to mind, and to Michael's point about all the different factors that an architect is considering, and this just being one touch point along the way to begin to think about. And one of those factors has to do with dimensional construction materials. And so, the lumber is dimensional. It comes in certain heights. And so there's, there are plate heights that you tend to see for floor to floor heights that are fairly consistent just based on the modules that are out there. The same thing with sheet goods of plywood, for example, coming in 4 foot by 8 foot. And therefore you could imagine there being, let's say, a difference between two dimensions that might seem, it'll save you some money if you come down to this height. But ultimately you just have more scrap and waste in construction to come to that height if it's an arbitrary height. It's just one example of the different criteria and factors that are going into thinking about considering all sorts of factors, including efficiency, not only in terms of energy consumption, but also in terms of that embodied energy of what's constructed. So I wanted to point that out. And maybe this comes back to now to the bigger topic. If you come back to maybe your very first slide, which is your title and or research question. I can't remember which was first.
Which one?
Okay, so maybe let's see. Okay, I think one big difference between the two strategies that you were suggesting is that one is more readily a retrofit scenario. Shading devices and overhangs could potentially be a retrofit scenario. The other one is more of a ground up scenario when determining the plate heights, the floor to floor heights of a building. So I think maybe acknowledging that, and maybe go back to the actual title of your thesis. And maybe that's even defined, maybe not within the title, but in how you explain this, of looking at two strategies, one that has more to do, is more generative and integrated in the entire design process, and one that's potentially a retrofit strategy. That's maybe one way to begin to describe these, because one, even if you were to find that these two strategies, if one delta were relatively the same as the other, one is much more costly to change or modify, or just can't be changed than the other. So I think maybe framing that with baking that within this and acknowledging that is valuable. That there's just an inherent difference in terms of the practicality and the application of these two That's very interesting. So it's and I think that's, I'm not saying that as a way to show there's a contradiction here, but rather that you're trying to address two different concerns, and that one might have to do more with a design process from scratch. The other one could be something you consider from scratch in terms of overhangs and just general self-shading in a building, or it could be something that could be more readily applied after the fact. So it comes back to circling back around to all of this and sort of comparing, as I'm just reading it myself again, like in comparison to architectural intervention strategies, ceiling height. And I wonder if it's even, if there is an operative verb that's more along the lines of optimizing, optimizing architectural form, and it had both to do with, overall mass ratio and beyond. I'm thinking out loud here a little bit. I'm just trying to make this something that is in line with what you're trying to do, but framing it in a way that potentially makes it more powerful, potentially, and then more of a reference point for architects to consider. I think then the other variable that was brought up by Dason that I just want to emphasize again is to do with the specific form that you've chosen, and acknowledging the limitation of that's just one form. But and I don't know again how much goes into modeling these different scenarios. But even if you were to just have one that were exactly half the size of what you're showing in terms of the volume to surface area ratio. If you slice that square in half, I don't know how much more work that is to do that, but I would imagine that as Dason's suggesting, you would see a fair amount of difference there. So those are just a couple of things that I can think of that might add a bit more to this, to round it out, to show you sort of intersecting a few different criteria without making it, letting this scope creep wildly away, which I know is your tendency to, because you're ambitious, you want to keep doing more and more and more. And so I think that those suggestions don't let this become a whole other project. They just allow you to go a little bit deeper with what you're doing, since you're asking for feedback in terms of what what else you might do to round this out.
And on that note, you said that when I agree with you that the ceiling height is more of a generative, ground up approach compared to the overhang, and that did cross my mind, and it made me wonder when I'm comparing the different massing strategies. Isn't it perhaps what would be a better software, the more comprehensive software would be to use a building information modeling system that does every single strategy and see how, because I focused on just two, but if I want to look at this instead of from a narrow focus, like you said, I shouldn't be so narrow, because as Professor Garrison said, there's hundreds if not thousands of different factors architects have to consider. In the using the BIM software, I can actually compare more holistically the ceiling height. And
I actually, sorry to interrupt, but I don't think you need to expand it to more and more variables. I think that the point that Professor Garrison is making that's valid is that what you don't want to do is for you to make a definitive conclusion based on this research, to suggest that having the overhang is better or worse, full stop. I think that's the important note, right? His point there, I believe, was that, go ahead, Michael, if you're gonna say something.
Yeah, you're right, you're getting it.
Is that, so it doesn't, so I don't think the suggestion was that, well, you should flesh out all of those 1,000 scenarios that are all there. It's rather suggesting here this is that's fine, which suggests what the relative impact is, which is stated here, in your question pretty early on, that you're beginning to define the impact so that one understands the impact and understands the relative change. So in order to make those decisions on a case-by-case basis.
I think another way of saying it is, you can say, this is what I looked at, these were the parameters, this is what the data told me. If one, but you must you just got to put a disclaimer in there and say, however, there are other considerations.
Right. Just two of the ones we mentioned so far in terms of daylight, so daylight factor or daylight autonomy, for example, or construction methods and materials, other factors that are considered as well. So I don't want you to take away, Robert, to be as though you need to take in consideration all those other factors, but just acknowledging the limitations of doing, and rather than having a qualitative stance on it to say this is definitively better way.
Yeah, that could have been a section actually in the thesis itself about limitations, and that you're not able to analyze spatial qualities and other issues, but somebody going further for future research might do that, and this could be a good springboard for that. But yes, no more simulations. I got an email late at night with how many were you planning to do when you were going to consider window wall ratio, everything, and it was thousands.
19,683, but
yeah, that's why we focused. Or he'd still be simulating.
But no, it's my own fault for trying to get as comprehensive as possible without understanding the fundamental basics.
No one can fault you for being ambitious. That's not the point. It is with any master's thesis, it's hard for everyone to narrow it down because you do want to do so much, but there's always, this is not the last thing you'll ever do. There's research in companies, there's research going on in academia further. So it's not your last piece of work.
Thank you a lot. This is very helpful because I do want to, I will fix whatever seems to have gone wrong, and I will. So I received the thesis. What I've written in the thesis was accepted, but they sent me a reformatting page that they want me to reformat, and my plan is that within the reformatting, I'll make sure that the results the numbers are fine. So it seems like they're giving me a chance to reformat before it's stored away in the Texas Digital Library for, in their own words, perpetuity. So I'll make sure.
That's a good question I had for Professor Ficus as well, if you might know. Do the students get a corrections phase after submitting their manuscript if they defend and then have corrections to make?
My understanding, no, I don't think so. I think my understanding is that that all happens between the student committee directly.
Okay.
The graduate school is more looking for just following fundamental standards, but they're expecting that the committee themselves, the committee gives them more, let's say, expertise or specific feedback to do with content. I'll say it that way. It has the versus format, and the graduate school deals more with format, and then the committee advisor and second reader deal more with content and just making sure that there's some cohesion to do with content.
Yeah, I'm just wondering, in cases where we had not a long time to read it, if there were corrections to make or feedback from presentations after. If in that case, Robert, I think you cannot change content. You just have to stick to changing format.
Okay. So there's no thesis errata form that you can add. There's no errata file, because I think errata files are.
You might ask Robin on that. I actually don't know.
It's worth asking Robin. I don't actually know either. It's been more of a formality in my experience, is that you need to just get that in there and check their boxes in terms of the formatting. Yeah, ultimately, at the end of it, and this is maybe a comment for everyone, is it's ultimately more important that you've built, you created a foundation of something that you could build upon or others can build upon. And as Professor Felkner is saying, this can be part of a larger exploration in your career that you build upon. That's the more critical part of the thesis, rather than the exact document itself and exactly how it's formatted or packaged. But really what what you've learned along the way, and then how you can, again, build upon that in the future.
Yeah, that's an excellent point. The people are the product, you all. So I think that's a good note to leave on for Robert. You have developed a lot and you've learned so much. So I'm really proud of what you've done, all of you.
Because of you all are the mentors, the guides, and help us.
All right. Well, I suppose we can sign off. And so, yeah, congrats to everyone for reaching a milestone. And
Thanks for getting us together, Matt.
Yeah, thank you. Good to see you all.
Yeah, it was fun.
Yeah, thank you everyone. Thank you all for your time. Thank you students for your work, and thank you so much for the review, tuning in and making some great comments. And thanks to Dr. Felkner for running the research design course and generally shepherding all these. I think you're directly involved in all these projects. I think, is that right?
That's rare. Normally I'm not, because I advise them to go out to other people. Yeah. But this year was a great group, and yeah, I held them all close. So it's been a pleasure.
All right. Well, goodbye, everybody.
Thank you, everyone. Bye-bye.
All right, see y'all.